Yeah. So it's 11 o'clock right now, so if people can take their seats, we're about to begin. I just want to introduce our session briefly. So this is a session on Beyond Species on the Move. We had talks yesterday, which were fabulous, and we're anticipating some fabulous talks today as well. There's also a poster session, and one thing to note is I believe we received 87 abstracts, which was really overwhelming, so many of them are going to be posters just because we're limited in terms of number of talks, so please do come to the posters. They are going to be terrific. I do want to also introduce my fellow co-conveners. So today I'm going to be convening Rebecca Ash from East Carolina University. Lauren Rogers is also going to be co-convening. Lorenzo Canelli is co-convening. He played that role yesterday. And our fourth co-convener is Manuel Hidalgo. So I do want to give you a couple just reminders. So when we break for lunch, you can go out that way or that way. So don't forget that lunch can be accessed either way. For people speaking, you're going to have 13 minutes. There's going to be a clock right here so you can keep track of time. We'll also let you know when there's 1 minute left, but please do try to stay on time. And then lastly, I am going to be introducing our invited speaker, which is Lisa Kerr from the Gulf of Maine. So I'm going to let her take the stage at this point.
Great. Well, thank you for inviting me to speak in this session today. I really enjoyed the talks I've seen over between yesterday and today. So I want to start from just an excerpt from the session description, and I kind of highlighted the two words that I plan to focus on today. A lot of my work focuses on the interaction between shifting distributions and how that intersects with the assessment and management process for fisheries, and thinking about how we can better integrate the information we're getting from all this great distribution modeling into our fishery management process. So I'll be drawing on a lot of my experience in the Northeast US, where I reside, and a lot of my work is focused. And this region is really marked by a very rapid warming pattern. We're outpacing the global oceans by almost 3 times the warming rate. And we're also in a region that's been characterized by increasing periodicity of marine heat waves. So we're seeing punctuated increases in warming, as well as spatial differences in the patterns in warming. 2022 was an interesting year. It was the second warmest on record, and also marked by a period of very extensive marine heat waves in our region. So with this warming trend and increased periodicity of marine heat waves in the Gulf of Maine, we're seeing impacts on our fishery resources, shifts in distribution, and changes in productivity in the region. And so on the left-hand side, you can see some information from the State of the Ecosystem report in our region showing an aggregate along shelf movement northward of species in the region, as well as the deepening over time. We also have forward projections in our region which show us we can expect more of this in the future, continued northward and northeastward shifts in distribution for our fish species. So we have, in addition to examples of shifting distributions for our fishery resources, we also see this in our fisheries. So we have examples of alter fishing locations. Here's an example for the large trawl fleet in the mid-Atlantic, which has shown this shift over time due to their targeting of specific species that have been shifting northward, specifically summer flounder and Atlantic croaker. In addition, in the work we do with fishers, we commonly hear from them that they're fishing in deeper locations than ever before. In our neck of the woods, we hear this a lot for our groundfish species. And at the lab I work, many of you probably experience this too. We get a lot of calls about, from harvesters about rare and exotic species that they've encountered, because they are kind of on the front lines of the shifting distributions into our region. So we have this growing number of examples of both observed and projected distribution shifts in our region. And NOAA in our region has really put a priority on trying to improve our ocean forecasts on the short term on scales that are relevant to our fisheries decision making. So they put this priority on providing more skillful climate and ocean forecasts with the goal of improving our fisheries yields and fisheries sustainability. So this is an example of ongoing work and the development of MOM6, or the Modular Ocean Model, which is being used to downscale global climate predictions for the Northeast US. So lots of work already documented and more skillful forecasts coming online in our region. Unfortunately, we don't see a lot of this information being integrated into the assessment and management kind of pipeline. And some of my work really focused on the question of how can we better utilize this information, and how can we help use that information to help us answer this question of how do we sustainably manage stocks as they shift their distribution. So in addition to the challenges that our fishery resources and fisheries are experiencing, our fishery management system is also getting this stress test due to climate. So this is a real simplified view of our US fishery management system. So we have information on our resource and our fishery that feed into the stock assessment. That gives us our estimate of stock status. And stock status is used to determine catch advice, which is then turned into or allocated as quota to the fishery, who implement it back on the resource through harvest. And so this loop is meant to be responsive to change. And although we collect climate and ecosystem information, oftentimes at the same time that we're collecting fish information, we don't see that information really well integrated, as well as social and economic information that we have on the fishery is not well integrated into our fisheries management decision process. And this can lead to a failure, this failure to account for climate impacts can lead to the potential for misleading stock assessments, which can lead to unsustainable catch advice, and you can have these conflicts between the allocation of catch and where fish are actually available. So one of the key issues is that many of our assumptions in our fishery management system are strongly linked to history and the concept of stationarity. So they're really designed assuming that environmental conditions will change gradually or change within some certain bounds, but not perhaps designed optimally to deal with this situation where there's a strong, rapid shift in directional way. And the consequences of not accounting for this can be particularly acute in areas where the change is happening at a rapid pace. So one of the places we see a particular challenge to stock assessment associated with shifting distributions is around the indices of abundance that we use to inform our stock assessments. So we typically use fishery-independent data from surveys or fishery-dependent data to create these indices of abundance, or CPUEs, catch per unit effort, with the idea that there's this proportionality between the total biomass of the stock you're interested in and your CPUE, or catch rate. So when biomass goes up, our catch rate should go up, and vice versa. But when you have these shifts over time and the availability of fish to a survey or fishery, this can really confound our interpretation of these trends. And these CPU time series are a real cornerstone of our stock assessments. So in our neck of the woods, we feel like we're seeing symptoms of some of the symptoms of unaccounted for climate impacts in the performance of our stock assessments. So what we find is an increasing number of our stock assessments have these issues or inconsistencies called retrospective patterns. The idea being that you add another year of data and you kind of look backwards and realize you were really wrong in your assessment of stock status. And we have looked at this in a kind of across stocks and actually found some synchrony in these stock assessment inconsistencies, which tells us that maybe there's a larger scale driver that's driving these patterns. And we found some associations with temperature indicators and stock assessment inconsistency. But basically, these are kind of a symptom of a problem. It's hard to definitively diagnose it from this information, but it tells you something's missing or misspecified in your model. So how do we better integrate information on shifting distributions into stock assessments? Well, I'm really interested in this question and finding these on-ramps to bring this information into the assessment and management process. So a lot of the work I'll describe today kind of happens under this banner of the Northeast Climate Integrated Modeling, or what we call NCLIME. This is a collaborative group with researchers from NOAA, Rutgers, GMRI, and UMaine, where I'm based. And the goal of the group is really to apply climate integrated modeling to improve our fishery resources, or fishery resource decision making in the Northeast US shelf ecosystem. And we kind of organize ourselves around these concepts of collaboration, innovation, and application. So the collaboration is developing a community of practice with scientists, working directly with managers and fishery stakeholders. The innovation is around simulation testing. So what are new ways of doing fishery management, and how do we think they'll perform through simulation testing? But equally important is the application space. So we spend a lot of time trying to move the science into fisheries management. And so I'm going to talk about application today, but I'll make a plug for innovation. We have a session on Thursday talking about MSE as a tool to establish robust fishery management in a changing ocean. And one of my postdocs under the NCLIME work, Amanda Hart, will be presenting a couple talks in that session. So in our effort to apply climate information in the context of a stock assessment, we've taken on this structured approach, and I'll kind of describe the steps. But basically, we're using this within the context of a stock assessment, maybe known as a benchmark stock assessment here. In our neck of the woods, we call it a research track stock assessment. So this is doing science to match management timelines. So we start out by characterizing the state of knowledge. So we do this with a science review and creating an ecosystem profile for a stock. We also engage with stakeholders and try to characterize fishers' ecological knowledge on climate impacts on stock dynamics. We then shift to developing relationships around climate, ocean, and stock variables. We do this exploratory modeling outside of the assessment, and then move to integrated modeling, so working inside the assessment and trying to integrate this information in that kind of model. And we see a lot of different applications for this work in the stock assessment. Some piece of, at one end, you could just be giving the modelers an ecosystem context for understanding data and results. It could be used to improve the actual model assumptions and parameterization. It could allow you to acknowledge non-stationarity in some aspect of dynamics, all the way up to having a fully climate-informed model. So I'm going to talk about two case studies that I've been involved with today. One on American place, so a demersal species. It's managed in the US by one of our regional fishery management councils. And the other, Atlantic bluefin tuna, highly migratory and managed by ICAT, or the International Commission for Atlantic Tunas. But both of these species has shown a shift in distribution, and both have used some climate-informed information in determination of catch advice. So this is one of my favorite phrases. I don't know if others get excited about this phrase, but I do. So trying to move climate fisheries information and kind of move it into the, to being actionable and used in management. So I'll talk about the place example. Here are some of the contributors to that work listed on the slide. We started our process by conducting this ecosystem profile, which kind of coalesces the best available science on climate and ecosystem impacts. But we do it really with a focused lens on what information feeds into the assessment and how can we characterize it at a scale that will kind of fit into this box of your stock assessment. But one of the things that did rise to our attention at this stage is there was evidence of, or there was some forward projections for place that would suggest that we might be seeing a decreasing trend in the future for place, particularly in inshore waters. We held meetings with harvesters through workshops, as well as conducting one-on-one interviews. And here are some of the bullet points, or just some of the common feedback we were getting at some of these meetings. But the thing that kept coming up for us again and again from fisheries ecological knowledge was depth is important for place. We're seeing changes in where we find fish. And so using the science review and our fisheries ecological knowledge, we went on to do some of this exploratory modeling using generalized additive models to try to relate some indicators of distribution change with ocean variables. And you can see this is a time series from just the trawl survey. You do see this dramatic shift in depth in the fall Interestingly, we don't see in the spring, which we think is associated with movement inshore to spawn for the species. And we did see some association with the depth change, the increasing bottom temperature, as well as NAO patterns in the region. But we wanted to dig into the distribution shift a bit further. We did this using a spatial-temporal model known as VAST, developed by Jim Thorson. And this allowed us to characterize distribution change and estimate kind of the potential drivers and importance of environment in that change. The other nice feature of this is it allows you to integrate data across surveys. So typically you have multiple survey indices going into assessment, and this allows you to kind of pull them all together into one index that has a potential to account for changes in catchability. So this is some of the results from the place VAST modeling. We can see there's evidence of a decrease in the effective area occupied by the place over time. There was this variable shift in the center of gravity over time for place. And what this counterfactual analysis showed us that depth is indeed really important. At the local scale, temperature did not rise as a key driver of changes in distribution, but depth was incredibly important. And we see what we can do with this is we can kind of compare our VAST indices of abundance, which are shown in green, with kind of our typical conventional indices of abundance and evaluate what the degree of agreement is. So we did evaluate actually integrating the VAST index into the assessment model for place. It didn't get accepted as the primary index, but we did actually use it to inform our selection of which indices move forward into the assessment model. So we ended up actually excluding this, the second state-based survey because it helped inform us that this is actually no longer a valid index of productivity. It's actually just showing us that there's a distribution shift, which is not what you want in your assessment model trying to predict overall biomass. And then we got to the climate integrated modeling for place. So we got to evaluate if including time varying processes in the model improved our model fit, and even tested some climate informed models that had direct integration of environmental covariates. We ended up accepting the time varying process model for our peer reviewed model, so the one that was used for setting catch advice. So this accounted for non-stationarity. Our climate informed model didn't quite rise to that level of acceptance, and kind of more a reflection of doing science on a management timeline. We had some diagnostic issues and couldn't put it forward to peer review, but these are the sort of the challenges in trying to do these things in strict amounts of time. So for American Place, we documented a shift in depth. We found some promising relationships with temperature in particular. We got to use information on shifting distributions to improve model assumptions and what indices inform the model, and actually got to a model that accounted for non-stationarity in some way by allowing for time varying processes. Our climate-informed model wasn't accepted for use in catch advice, but we were able to document it so folks can pick it up in the future and potentially use this going forward. So I'll shift to our Atlantic bluefin tuna case study. The collaborators here are listed below. And tuna is a species that's managed as two distinct stocks, east and west, split roughly at the 45-degree meridian. And although we know fish can move across this boundary, we actually do stock assessments that are distinct. And because tuna are so highly migratory, we rely on a lot of fishery-dependent data to inform these assessments. So that's what you see here. Typically, it's country-specific, fleet-specific, and you get these indicators of what you presume is productivity. So what happened for us in 2017 at the bluefin tuna stock assessment is we were dealing with this conflict in signal between our Canadian indices and our US indices. Are telling us completely opposite things about what's going on with the biomass for Atlantic bluefin tuna. Ultimately, we had an unfortunate result of actually the data had to be thrown out because we had a very inflexible model at the time that couldn't accommodate this conflict. So that's really not an optimal result, is removing data. But it did flag for us that this was an area that needed some research to understand so we could better accommodate it. And at the time, we hypothesized this was indicative of a northward shift, not really an indicator of productivity of the stock. So we worked on constructing an ecosystem profile for bluefin tuna. For a very economically important fish, there's actually not a ton of research on bluefin tuna, but there is a pretty good literature on movement due to tagging and observations of tuna. And so we know that we knew there's some relationship between the complex movements of this fish and climate and ocean variables, as well as prey distribution being very important, particularly in our area, which is a key forage habitat for bluefin tuna. And we also know that their key prey items like herring and mackerel are highly influenced by ocean climate conditions like temperature, chlorophyll, and sea surface height. And that's what you see here. This is a heat map of herring, and you can see the little white dots there are the occurrences of bluefin tuna in a high degree of association with their prey. So bottom-up control is important for these guys. We also characterize fisheries ecological knowledge. So because when you're working with fishery-dependent data, you want to really understand what is driving the trends in the data, and so you're not making ill-informed conclusions or coming to ill-informed conclusions. So during the workshops with fishermen, we identified potential factors influencing indices of abundance coming from their fishery, and they really flagged that ocean conditions are changing, and they think it's changing their catchability. But they also flagged some other interesting things. I don't know if folks know that in New England there's a reality show called Wicked Tuna, which features the fishery, and the fishermen, the kind of core fishermen, think that this has really introduced a whole lot of inexperienced fishermen coming into the fishery and lowering their CPUE, which is kind of interesting. So it was something we were looking out for, trying to test for. And they also gave us some good information about the appropriate geographic scope for defining their index for their fishery and the appropriate effort metrics for characterizing effort for them. So here's some of the we also embarked on some distribution modeling like we did for place. So we're using generalized additive models and VAST, again, to look at the spatial-temporal changes in distribution of bluefin tuna. A thing that we'd hoped to do here was integrate US and Canadian data together so we'd really account for that shifting distribution. But as we spoke with fishermen, we were speaking with both US and Canadian fishermen at the time, we realized how very different the fisheries are fundamentally and how different the data collection is, which kind of resulted in us tabling that idea to a later date because it really became out of scope to resolve that in the construct of the model. But we were able to work on improving our US indices of abundance and accounting for sea surface temperature influences on the local catchability. And so these are some improved indices that came out of spatial-temporal modeling for large and small tuna in US waters only. But again, we still had this issue with a shift from the US to Canada to deal with. And here we had the advantage of using stock synthesis, which is another flexible assessment model platform that allows us the flexibility to include things like time-varying processes or include an environmental covariate in your model. Here we included AMO, which was used to modulate catchability and significantly improved fit, and my favorite phrase was used to inform catch advice, which is really exciting to have. There's not many examples of climate-integrated models out there, So anyway, for bluefin tuna, we identified this northward shift in distribution associated with sea surface temperature. We were able to improve our model assumptions, including some climate information, and just standardizing our indices and trying to account for these changes in catchability to some degree there, and also got to the point of having actual climate-informed model that was able to better account for shifts in distribution in the construct of the assessment model. So, I think having this structure really helped us, to be focused in working in, trying to do science at a pretty rapid pace within a stock assessment process. For place, our process lasted about a year, and for bluefin tuna, it actually spanned a couple of assessments, so it's more along the lines of a couple years. But it definitely helped us move through the different steps and ensure that we were scaling information such that it could really flow into the models we were working with for these particular species. And I think it's just exciting to think about how to better utilize the information that we've seen in all these talks today in contributing to sustainable management of our fisheries. I'll just end today with a couple things that I think helped us in the process and we learned in kind of trying to work in this space. It's really key to identify these on-ramps for climate fisheries science in assessment and management and try to, work towards moving data into that pipeline, participate. So attending these meetings, participate in assessments. There's a lot of time involved in doing that, but that's really the only way to get your data and information integrated. Using a flexible assessment model, so WAM, a state space model, and stock synthesis allow for climate information to be integrated. Without those tools, we couldn't do this kind of work. Scientists' willingness to work on management timelines. There's this inherent tension of getting it done and getting it right that can be an uncomfortable space to work in, but you have to kind of be willing to try to keep pace to hopefully improve the information going into management. And then one of the big things is we were able to do this by bringing interdisciplinary capacity to the table. So bringing ecosystem scientists into the stock assessment process and bringing postdocs and graduate students into the process was a big part of how we got this work done on such a fast timeline. So I just want to acknowledge my funders for this work, NOAA's Climate Fisheries Adaptation Program and the Bluefin Tuna Research Program, additional collaborators, and I'd be happy to take questions. Also, there's so many smart people here that I don't want to lose an opportunity to plug that I'm looking for a postdoc. So thank you for allowing me to speak today.
We have about 2 minutes for questions. And I'll bring Mike over.
Hi, good morning. Very interesting. Just a quick question regarding your place model. You said that depth was important, but not temperature. I have a two-way question. What kind of temperature is it? Bottom, surface, whatever? And I would think that, changing depth means also changing temperature. So.
Yeah, we were exploring bottom temperature for a place, and I think it's just a question of scale. Sometimes we were finding at the aggregate scale when we were looking at, say, the generalized additive models, where we had these aggregate indices of shifts in depth, we were seeing stronger relationships with, these temperature, like things like bottom temperature. But then when we were looking at the very fine scale, spatially explicit data, that didn't come through as much. And I think there's different processes going on here, and so I think thinking about scale and how local conditions are influencing changes in distribution versus kind of the aggregate experience and regional experience, you can kind of get sometimes conflicting messages there. But I think it's a question of scale, which is kind of important to disentangling what's driving catchability versus what's driving productivity. But, yeah.
So we have time for one more question. Anyone have hands? Okay, I see one back there.
Hi, so you mentioned for the place model, you used the kind of the WAM random effects model, and you called it non-stationarity, but did the random effects actually show a trend in time in some variable, or maybe I missed it, or is it just kind of random variation?
It was random, yeah, it was random variation. So it was counting for some, the only slightly unsatisfying thing about random effects is that you don't get this mechanistic link, and so it kind of sucks up a lot of, time, can suck up kind of multiple time varying processes in that, and like accounting for that. So it adds this flexibility to the model that's not as rigid, and so you're not getting these retrospective patterns that we traditionally get. But diagnosing and disentangling what factors are being accounted for, is it unaccounted for mortality or movement of the fish? That's kind of a little bit of a black box, yeah.
Okay, so we're going to transition to our next talk now. This is going to be Elena Couce. And thank you, everyone. and she is coming to us from CFAS, and she's going to be talking about coral reef diversity forecast for warmer and more acidic oceans.
It's on.
Opportunity to speak today. And so I'm going to talk about coral reef ecosystems. And you probably already know, but this is one of the ecosystems that is more sensitive to climate change. And the problem with coral reefs is that they get a bit of a mixed signal from the environment. Okay? And so we have, on the one hand, we have warming. And warming, basically, what it does to species that are sensitive to heat is that it pushes them away from the equator into higher latitudes when it's a bit colder. But coral reefs are a bit weird as an animal, because in addition to being an animal, they are also a bit of a rock, because their skeleton is a rock. So they have to create this skeleton, this rock. And this creation of the aragonite, which is the crystal name of the calcium carbonate that they produce, that's very sensitive to acidification. And acidification is kind of the opposite, in the sense that it's easier at high latitudes, because it's favored by low temperature. It's the CO2 of the atmosphere dissolving into the ocean, and that's easier when the temperature is low. So it happens at high latitudes. So basically what it's making for corals is that it's making it difficult for them to create the skeletons at high latitudes. And as this progresses in the centuries, it's going to actually shrink the habitat towards the equator. So yeah, it's a bit complicated to decide what is going to happen to the coral reefs in the world. And actually, that's the question we all want to know, what is going to happen to them. But that's not the question I'm going to answer today. Because it's a very complicated, very difficult question. So I'm going to simplify it a bit. And basically, I'm going to talk about what the environment is going to, how the change in the environment is going to drive the potential habitat. Okay? So it's not exactly the same question, but it's a good starting point. And so we know where coral reefs are. These are tropical coral reefs I'm talking about. So they are found at low latitudes. And they are generally in very shallow waters, so we can pretty much see them from satellite images. I mean, we know where they are. And that's pretty much the locations that I work with. And the problem is, it would be lovely to have a list of the species, the coral species that are found in each and every one of these reefs, but we don't have the data. And however, for each coral species, we have a rough idea of where they are found. Like, for example, I'm going to give you some examples. And that's a species that is found in the Coral Triangle region, mostly. And this other species is found a bit wider in the Pacific Ocean. Another one that is found in other places. So roughly, we know where they are, okay? And the thing is that probably there is a reason why they are found there. Each particular species is found where they are found and not. So it's probably the environment that is determining where the species is found. So things like temperature, aragonite, of course, nutrient levels, light availability, the speed of the current, the dust levels, the frequency of storms, all these kind of things. So once we look at this and we look at where the species are, we can create some sort of statistical model. And we try, when we give it the future data, we can predict what the habitat is. Okay, so these are our species distribution models, and everybody in the session has been using them, so I'm not going to explain what they are. You already know. But that's what we did. And we did this for 710 different coral species. So these are the details. We didn't assume the species was present everywhere throughout the range. We assumed it was present something like 70% of the sites there. But we thought that the range at least would capture the environmental preferences of the species, okay? So we used all the reef in the range to train the models, but we constrained the prediction, the projection, so only 70% of the sites would actually predict the presence. And we also took into account connectivity, because obviously a species can only be where it is at or where it could potentially get to. Most coral species are spawners, so they produce larvae that get carried by ocean currents and can travel quite far. Some of them are not. Some of them are brooders, so they actually reproduce quite close to their original parent. So for the spawner species, we took into account the ocean connectivity, and we trained the model only in areas that the species was found at or it could potentially reach. We look at two different futures, one that is more or less like the Paris Agreement, and one that is high emissions. And we projected what it was going to happen to them with max sense. And so this is what we found. And I apologize on behalf of the models because the projections are really dire. And so on the left-hand side here, you have Paris Agreement. On the right-hand side, you have high emissions. And you can see, basically, the light yellow colors mean very high number of species, coral species. So you can see in the 1990s, you have the coral triangle is really yellow there. And you have greens, and you have blues, and yeah, there are some darker colors. The Caribbean is very low diversity. But you can see what's happening here on the Paris Agreement and high emission futures. And this is just 2040s, 2080s. I mean, I'm not looking very far into the future. And you can see that it's all dark colors now. It's all purples and a little bit of green. On the Paris Agreement, you have some green still in the coral triangle, but nothing like the yellows we had before. Okay? So basically, we're seeing a very high loss of coral regions nearly everywhere. And so this is another way to look at the results. We focus on particular important coral regions. So things, coral triangle, the Red Sea, the Central Indian Ocean, the Western Indian Ocean. We have the Great Barrier Reef and the Coral Sea in blue. And then we have the Caribbean in purple. So that's basically looking at alpha diversity, so the average number of species in each particular reef. Okay, and you can see what's happening under Paris Agreement on the left side and on the high emissions on the right side over time. So it's going down a lot, practically everywhere. And the Red Sea is actually doing better than others under the Paris Agreement. But yeah, it's not good. However, if we look at gamma diversity instead of alpha, things look a little bit better under the Paris Agreement. It looks still terrible for high emissions. But this means basically that the species are still present somewhere within the region. So it's just becoming more heterogeneous. So you have a different number of species, different species present in different reefs within the region. And this is actually good news, because under Paris Agreement, things start improving mid-century. Temperature starts coming down again. So if the species is still present, not too far away, it can still repopulate when conditions get better. So if they are gone from the region, that's very bad news, because it's complicated to imagine how it can come back. But if they're still there, if it's still hanging on there, then it could potentially actually start coming up again towards the end of the century. Okay, so this is not a terrible result. So I focus on this part because it was the only one that was not terrible of my projections. So yeah, under the Paris Agreement, you have like 0 to 30% loss of diversity in the regions that I look at. And yeah, mid-century, you have some recovery. We also look at functional diversity. And so basically, coral reef species play different roles in the ecosystem, and depends on the shape and things, and the way that they are. And they're also sensitive to the environment in different ways when they are different shapes. And so this is only the results for the coral triangle. But you can see what is going to happen with Paris Agreement and high emissions. So you have the gray dots. Those are the present-day projection, all the species that you have in the present day in the trade space. Okay? And you can see how that trade space is going to shrink under Paris Agreement and high emissions. And same thing here. You have the Paris Agreement and high emissions, and you can see how many species we used to have in the 1990s versus what we're going to have in the 2080s for Paris Agreement high emissions. And you can see what a drastic difference it does make, the high emissions versus the Paris Agreement. And so it's not only you don't have redundancy, you have a lot less species representing each of these morphologies. And it's also if you have a high diversity region, obviously the coral triangle is not a high diversity region. But if you focus on a low diversity region, you find that some groups are completely gone in the future. So that's obviously going to change the ecosystem functions that they can provide. So things like coastal protection and the species diversity they can maintain in general. All right, so basically, to summarize, we have significant declines in species richness pretty much everywhere. And this is something like 73% for Paris Agreement to 91% for high emissions. Okay, so it's really, really high. And this is particularly important for sites across the Great Barrier Reef, the Coral Sea, and the Western Indian Ocean. But at the regional scales, there is a bit of hope, I think. So the losses we have is this between 0 and 30% for most of the regions we look at, and that's compared to 80 to 90% losses under high emissions. So I would say it's critically important for corals that we keep warming very close to Paris Agreement. I mean, they are really not doing well now, and if we have a very high degree of warming in the future, I don't think they are going to survive. And SDF models, they can provide an indication of what the future climate is going to, what it's going to mean to corals. Okay, it does not predict coral response. I cannot tell you that the species is going to die if the conditions get bad. Some species may hang up a bit longer, some species may actually die sooner because they have bleaching and things like that I'm not considering here. But still, they can give an indication and they can start answering this question. And so if you are interested in this, I actually have a bit more details in this paper that is coming out tomorrow, so almost perfect timing. So yeah, if you want to, you can click there. So thank you very much.
So we have plenty of time for questions. Okay, I see several of them, so I'll go here first.
Okay, thank you. Yeah, well, that's a very depressing thing to see,
sorry.
but I know of, I mean, there seem to be many efforts to grow coral, little pieces of coral and stuff. Are people trying to do experiments to select for warm tolerant or acid tolerant species, or genes, I guess?
There is a lot
Are they
of,
doing that
going on.
to restock out in the wild?
Yes, thanks for the question. There is a lot of that going on, yes. And so they are trying to see if some particular species are less sensitive to heating, and they can actually use these species to populate areas that are most impacted. They are also trying to see, because the heat resistance of corals is very much dictated, at least partially, by the zooxanthellae that lives in their tissues. And so you can have different clades present even in the same corals. In the same individuals, you can have many. So some of them are more susceptible to heat, and these are the ones that cause bleaching. So if you could actually shift to the other clades, that you could possibly gain some heat resistance. So we're talking about, I don't know, half a degree, 1 degree, I don't know, a little. But it's probably not going to be enough with that. So there is a lot of that going on. But I just think it's like a bit using a Band-Aid to try to stop serious bleeding. I don't think it's going to help a little, but I don't think it's going to be a solution to the problem. So.
Hi, thank you for a very informative talk. I was wondering, you compared the coral distribution from the 1990s,
Yeah.
and then 2040 and 2080. But is there any way that your data could tell something about how the model would perform from 1990 to 2020? Or is it just not enough information to say something about the change between 1990 and today?
The problem is that the corals are dying for bleaching. And it's not exactly something that the model is looking at, because I'm not modeling bleaching. Bleaching is a response to stress, to short-term stress. And that's really difficult to predict long-term. So I cannot know what the heat waves are going to look like at the end of the century. Basically, we don't agree. The models don't agree on these short-term predictions. So it's very difficult to project how, because the corals are now dying from bleaching. And how is that reflected? We don't know what the species are changing distribution. We don't have that data. Okay. We don't have the surveys going on every other month and just looking at the species that are there or not. So we know there is a lot of reef damage. Some of them come back, some of them don't. It's very complicated to actually see how the distribution is shifting in real time, because it's not like fish that you can just do a survey and see if it's there or not. The corals, they tend to die in areas, like all the species die, but some of them come back, some of them don't come back. It can be several years. And we don't have that real-time data on the response. So that's why it's very complicated to model as well.
So I think we have time just for one more question. I think
sorry.
I saw your hand first.
Thanks for the talk. To what extent do you think that species interactions could change the predictions of your models?
And yes, I did not take into account species interaction. And the problem is that it's also very complicated to take into account species interaction, because this is a bit like a tropical rainforest. You have so many species present, and it's a bit complicated to know how they are we know some coral species fight with each other. There is some chemical warfare going on there. There is some other species that can coexist, but there is not wide available information of what all the species are doing to each other. So I don't really know which ones support and which ones don't. And it's not easy to get that information considering we don't really have data of the species that are normally coexisting in reefs. So this range that I show for the species is pretty much the only information there is of where corals are found. You will probably require data at the reef level to actually know all the species that are there and have that for a very large, many sites in the world, not only one site as well. And then that could start answering that question. But it is not easy to include the species interaction for coral reef species itself. It's just not yeah, it's a very interesting question. I'd like to be able to do that, but it's just not.
So I think we do need to move on to make sure there's enough time. So thank you, everyone. And our next speaker is going to be Owen Liu. He's coming to us from NOAA.
Hi, everyone. Thanks for being here. I don't know if anyone else has noticed, we've had significant climate change in this room, so thank you for sticking it out with me. On behalf of my co-authors that you see here, today I'll be talking about species redistribution in the California current and some outcomes for multi-species fisheries under climate change. So thank you to Barb and actually to Lisa as well for kind of teeing up a lot of the introduction that I was going to give. But we all know warming, changes in productivity, things like ocean acidification and deoxygenation are all causing marine species to shift where they're distributed in space. And there's obviously a lot of growing interest in projecting where these species are going to be in the future based on their sensitivities to these environmental changes. And I would argue, actually, that as you've seen today and as you'll see for the rest of the week, that our models to sort of predict species distributions and project them are growing very rapidly in sort of their sophistication, their flexibility to different sorts of problems, and their applications even all the way into the management pipeline like Lisa was talking about. And I would argue that our ocean models and our downscaled ocean models are improving all the time as well. This is oceanographic projection data that I'll be using today from Mayor Pozobuil and Mike Jaycox and colleagues at the University of California, Santa Cruz. And in the California current, like many areas of the coastal ocean, we're expecting significant warming and deoxygenation across different models by the end of the century. And again, as we've seen this week, climate change could have different effects on different species. Species could be sort of differentially sensitive to different sorts of environmental changes, and this could lead to new ecological interactions. But more what I'll be talking about today is that this could cause new fishery management challenges as well. So particularly in unselective multi-species fisheries like trawl fisheries, where you're sort of catching all the species at once and it's hard to target individual species. And so in a multi-species context, if species are reshuffling in space, then you could have new sort of challenges arise. And I'll give you a quick example. Say you are targeting this high-value species that undergoes a climate-driven shift to the north, and all of a sudden it is caught or it is associated with a large abundance of a much lower value species. And you could imagine that this could cause a number of different management challenges, including if you are someone that is targeting the high value fish, all of a sudden it becomes harder to target because your nets are filling up with this highly abundant but low value species. And on the other side, if you are targeting the low value species, you could be constrained by your allowable quota or by bycatch issues because you're worried about catching this species that has just recently moved into your area. And so that leads me to the key questions for this talk today. We're interested in how climate change will affect California current ground fishes out to the end of the century, and how might these changes affect fishing opportunities for US West Coast fishing communities. In this work, we focused on what's called the DTS, or Dover Sole Thorny-head Sablefish Complex. On the West Coast, this is a common set of 4 species that are caught together in the trawl fishery, where sablefish, or black cod, some people may know it as, is often the target and the most valuable species. In this revenue time series on the right, that top line there is the sablefish landings. And you can see that it's more valuable in most years than all of these other species put together. And so it's really the target valuable species. And as we've already seen, there's a significant environmental change projected within the California current. And so what does this mean for how these 4 species may reshuffle themselves in space? So you've heard a lot about species distribution models. The one we used is called SDM-TMB. For those of you in the session yesterday, Eric Ward introduced this in the very first talk. And they are generalized linear mixed models. And we fit them to trawl survey data with the modeled UCSC ROMS data from Pozobwil and colleagues. And then we projected them out to the future, and what you get is a spatial prediction of CPUE or density that looks something like this on the right. We modeled each species with an ensemble of multiple models, where each individual model, we varied our assumptions about the functional form of the relationship between the species and the environment. So we varied our assumptions about species density versus temperature, or species density versus bottom oxygen. And then we sort of gathered all of these individual model predictions into an ensemble with individual model weights determined by likelihood-based model fit metric from cross-validation. And we did this with the 4 species under these 3 Earth system model projections. And so jumping right into the results, the first thing we might be interested in is sort of overall indices of abundance. So you see here on the y-axis, this is an index of abundance. This is projected time here, and each of these individual lines is one of the Earth system model projections. And you can see that for sablefish and short-spine thorny-head, these 2 species are likely to decline in abundance, and that's pretty consistent across models or across simulations. Whereas long-spine thorny-head is likely to increase, that's the one on the bottom. And Dover sole is a little bit more uncertain, but at least under the GFDL and IPSL projections is expected to increase in abundance in our models. And so you could ask next, given this change in abundance, what's the expected change in sort of spatial distribution? And so what I'm showing here is latitude on the y-axis, change in distance from shore of the sort of centroid of the species distribution, if you will, where to the right is further offshore, to the left is further inshore. And the point of showing you this is that especially for Dover sole, sablefish, and short-spine thorny-head, and especially towards the northern part of the California current, we're expecting a significant shift offshore, which you could imagine could make fishing more expensive or less efficient. At the same time, we have you can imagine that a shift offshore would also be associated with a shift in depth, and that's exactly what we see. These are cumulative depth curves with depth sort of going down on the y-axis. And again, you can see for sablefish and for short-spine thorny-head, we expect a significant deepening of the species distribution. And so finally, we want to ask, what implications does this have for West Coast fisheries? And for those of you that were in session 9 yesterday and saw Jamil Samhouri's talk, he talked a little bit about these fishing footprints, but we took spatially explicit logbook data, and we assessed these sort of fishing home ranges out of major West Coast fishing ports. So these are areas where this complex of species is caught now. And we could ask, so within these fishing footprints, how is the environment likely to change, and how is the species availability likely to change? And I'll just give an example for sablefish here, and you can see that from north to south in these ports, sort of consistently across them, we expect to see a 20 to 40% or greater decline in availability, again, within the areas where fishing occurs now. And then finally, back to the sort of toy example I gave earlier about changing overlap between species, we calculated a measure of statistical affinity between species distributions using Bhattacharya's coefficient. And then we measured how that overlap metric changes over time. And that's what you're seeing here is the difference between sort of end of century and current day. And you can see that within these circled, the two largest fishing footprints, that there's actually expected to be a decline in the relative spatial overlap of these two species. And so then you might ask, is this kind of a net positive or negative for fishers and fishery managers? You could imagine with a decline in overlap, you could say, oh, that each individual species may be easier to target, so we can choose to fish sablefish or we can choose to fish Dover sole. But given the other things I've talked about today, the decline in sablefish and its redistribution to deeper water, this could definitely offset any gains you might be able to gain from cleaner targeting, if you will. But on the other hand, Dover sole may become easier to target. As we saw, it's expected to increase in abundance in a lot of places, and combined with a decrease in overlap with sablefish, may become easier to target. And but the ultimate sort of net result of this for fisheries is obviously going to depend on market conditions, prices fishers can get for these two fish, and how that may change over time. So to move to my summary, we expect significant environmental change within the California current, which will affect species distributions. Most distributions that we studied of this complex are projected to be deeper and further offshore than today, moving away from current day fishing footprints and potentially making them more difficult to target. There's corresponding kind of lower projected fisheries availability for these most important species, at least within what we think of as current day fishing grounds. And changing climate will cause changes in the co-occurrence or overlap between species, and this could lead to potentially new management challenges. And taking one step back, as I mentioned at the beginning, I really think our oceanographic projections and our SDMs are really getting better all the time. And so our need now, as Lisa touched on as well in the first talk, is to sort of connect the hypotheses that are coming out of these models to implications really for fisheries and for practical management. And I think that's kind of where we're going now, with the ultimate goal of more sustainable, climate-resilient fisheries and fishing communities. So I'll say thank you, and this work was funded in large part by the Packard Foundation as part of the GC5 project at NOAA. So thank you.
Okay, we have time for a couple of questions. I think maybe only just one question, but okay, I see a hand up over here.
Thank you for that talk. It was really nice, well presented, and I think I understand. But I just was wondering, since you have the temperature and oxygen together, have you put that in sort of in a metabolic index? And wondering if modeling those data under that construct might show that there might not be a switch to deeper water. And anyway, just what your considerations are, since it seems like you have the data to do that.
Yeah, no, that's a really good question. We definitely considered it. I personally don't have a lot of experience with a metabolic index, although I know that, I know about it, but I haven't included it in this model. I agree with you that I think there's more sort of exploration to do to see if we're really pushing, because I specifically, for example, didn't include depth in my models, right? So often when you include depth in species distribution models, for those that have done it, depth ends up soaking up a lot of the variability, and sort of everything is kind of depth related. And so I do think for these species there's more work to do to really figure out which are the really key environmental drivers. But I think that one step forward we did make in these models is including bottom oxygen from the oceanographic projections, which is an improvement on former model or previous models that mostly just used temperature.
Thank you. So I think we're going to move to the next talk, but
Thank you for your talk.
Thank
Our
you.
next speaker, we're going to move on now. We can. Thanks. Our next speaker is Max Lindmark.
Yeah, okay. I'm Max Lindmark. I'm a researcher at the Swedish University of Agricultural Sciences in Sweden. And I would like to thank the organizers of the conference and the session for the opportunity to come here and talk. And my talk is about, not so much about range shifts per se, but like local biomass dynamics in response to climate change. And I'm looking at oxygen and temperature and the metabolic index that we heard about the other day. And yeah, it's, as you know, it's important to understand range shifts. They are key drivers of community reorganization in future climates. And yeah, we often use kind of aggregated metrics to look at that, like center of gravity and these things, and they can be very informative in many cases. But also in other ecosystems and systems, we need to think a little bit differently. We heard yesterday about sort of light limitations to northward distributions and those kinds of things. And where I work in the Baltic Sea, they're not limited by light. It's not that far north, but probably salinity. So if you go from the southern Baltic Sea, you have basically a marine system, and then as you go up north, you end up in a lake, more or less. So they're quite limited in salinity, and probably other things as well in their northward distribution. But yeah, so they're probably limited. They can't go north, really. But there's still a lot of change here. It's a rapidly warming ecosystem, and there's a kind of a big expansion of hypoxic areas in this ecosystem. Which is also why we want to look at the metabolic index to see, because it seems like a good case study to test that. It seems like that, but I will not promise too much. It seems perfect, but it's, yeah. And yeah, so that's the setup. We have identified a few questions we want to address. First, we want to look at the metabolic index, and then also trying to see if we can detect if species are avoiding these changes in the environment or if they're soaking it up, so to say. And then we have two sub-questions related to like species variation, life history, life stage, I mean, and at what scale we should look at these sort of responses. And luckily I have collaborators, so I'm optimistic we'll solve the remaining issues here with this work in progress. It's a really good team. And okay, so how do we do this? I am pretty inspired by these two papers that came out last year. They're really good. Felina English's paper here on basically a framework for modeling local changes in biomass in response to local magnitudes of climate change. And also Tim Essington's paper on the metabolic index and how we can incorporate that into species distribution models. So basically, you can imagine two kind of paths here for the approach. So first we do species distribution modeling with different covariates and see, okay, which variables are parsimonious in a way. It's kind of straightforward. And then we also do the sort of English approach to model species distributions, predictor distributions, and then look at the trends in biomass, local trends, in relation to local trends in the climate, and then fit spatial models to those kind of layers of trends. And I'll talk more about that soon. But first of all, we need to get metabolic index parameters. And this is an equation from Essington. It's rewritten from Deutsch's work. And yeah, it basically shows that the metabolic index is an allometric function of body mass, and it scales with temperature according to some Arrhenius-Boltzmann equation that is centered on a reference temperature. And if you know the critical oxygen pressure or concentration, basically the oxygen where you are 50% likely to survive 48 hours, like the lowest oxygen you survive, you can calculate this phi. And in the Baltic Sea, we don't have that much experiments. I've looked in the literature, and I found this paper it calculates this critical oxygen that we need, but it doesn't do that over a mass range or temperature range, which is ideally what we want. So I've just used Tim Essington's parameters and sort of mass and temperature corrected our critical oxygens. And then we can get like species and life stage specific metabolic index predictions. So the species distribution models are fitted to data from the Baltic International Trout Survey. I've used data from '93, and it's just biomass density of species, and I've split them by life stages. And the species there are flounder, European flounder, plaice, dab, and Atlantic cod. The models we use are GLMMs with spatial and spatial-temporal random effects using the SDM-TMB package that we heard about, and can really recommend it. It's super user-friendly and nice to work with. And we have these. So it's a GLMM with these kind of omega and epsilon, and I'll talk about them soon. For the trend analysis, we use model predicted oxygen and temperature from this NEMO Nordic model, and we calculate trends in space, so that's basically the change over time, and then also velocities to sort of take into account that some areas are really just warming and the species would have to move a lot to avoid that warming, whereas in areas with more heterogeneous distribution of warming, you wouldn't have to move that far, and that would be reflected in the velocity metric. But I'm not going to actually talk so much about that. I'm going to focus on the trend analysis, but it's quite similar anyway. All right, so for the first aim, I don't really know if the metabolic index is a more parsimonious predictor. What we have found is that oxygen and temperature as an interaction is pretty good, and we see very clear, in most cases, results that biomass is positively related to temperature only if it's enough oxygen, and if it's low oxygen, warming is really bad, or temperature is bad. We are working on sort of sorting out the metabolic index. I'll talk about that later. So I'm not going to stick too long on this. I'm going to focus on this result instead, which is how are species avoiding climate change, so to say. So in the top figure here, you see the dotted line, dashed line. It's the environmental temperature. And then the other colored lines are temperature in the environment weighted by the local predicted biomass density. And what we can see here is that they largely follow the environment, even in the sort of colder dip there around 2010. And you also see that in the bottom plot where I've correlated the environmental temperature with what the species kind of experience on average. And except for DAB, the correlation is pretty high. But DAB is also a special case because it sort of has become more abundant in this region, but it's still not very widely distributed here, so I think it's just a matter of that. And we see the same for the metabolic index. It's quite good correlation with the environment. We also see that the flatfishes have a higher metabolic index than cod, and juveniles larger than adults. And this is a combination of two things. So it's their distribution, which affects what they experience, but also that flatfishes are more oxygen tolerant, which we see from experimental data. Okay, so does this mean that climate change doesn't affect their distribution? Not sure, so that's why we looked at the local analysis as well. So this is models of trends. We model trends in biomass now in space with a spatial model, and we let the trends interact with sort of the local average environment, because we see here it's very heterogeneous where we have higher temperature, low oxygen, etc. So this is a covariate, and this is a covariate, the temperature trend, oxygen trend, metabolic index trend. Okay, so from these spatial models we can make predictions, and that's what I've done here. So the distributions here depict sort of delta biomass trends, and I do it for a 1 standard deviation increase in temperature. And if warm areas are smaller than the blue ones, that means we have a more negative effect in areas that are already warm when it gets warmer, and vice versa. And here we see 6 of 8 species kind of have this expected prediction that biomass goes up in cold areas with warming and declines in warm areas. And maybe that's why we don't see this population level change in sort of experienced temperature or shifts. But there's a lot of things going on here, I think, in the system. We can do the same for the metabolic index, but now instead of increasing, the metabolic index will decrease because that's what's going on. This pattern is a little bit more difficult to explain, and it just reflects that we need to do some work to understand the distribution in relation to the metabolic index, and that's, I think, basically partly related to depth, like we saw with the sablefish, but not as much because it's only like 100 meters deep here, not 1,000. And mainly that we have really high metabolic index values in areas where we don't have any fish at all. And I think that's just sort of confounds the issue, so we're looking into it. But so far we're pretty happy to conclude that, we are comfortable concluding that on average it doesn't look like the species are avoiding that much. They're not just moving around. Because when it gets warmer, they get warmer. But we do see local trends. And it's kind of not very sensitive to whether we look at trends or velocities. But again, what we're still working on now is sort of why this metabolic index behaves like it does. Are we missing covariates, or is it simply that way it looks? And if you have any ideas or feedback, we can talk after. Okay, so thank you for listening.
Thank you very much. Any questions for Max?
Thank you for a very nice presentation. I'd like to talk to you after the talk or the session. But I was wondering, with your when you did your weighted temperature in a way with your catches, did you actually have the bottom temperature where you caught the fish? I assume it was a bottom trawl service.
Yeah, actually we used model predicted, so we just linked catches to the sort of layer of temperatures. And that's because we want to calculate trends and velocities, and then we need a complete grid. I haven't looked too much into it, whether or not it's a difference between measured temperatures. Because it's an international trawl survey, it's a little bit hard to dig out all the old data, but that's something I want to look into. Yeah.
Another question? Somebody? Ben has a question about metabolic index.
Just sort of, maybe I missed it in your slide, but did you have a sort of a time series of the metabolic index over time in terms of just aggregating? Is there a pattern? What's happening in the system? And I'm sorry if I missed it.
Oh yeah, sorry. Yeah, it's a little bit harder to plot because each species and life stage combination will have its own trend because they have different biomasses and parameters. So it's not as easy to plot as temperature, but there is kind of the same pattern that the environmental metabolic index follows that of the species. If that's what was your question, maybe it wasn't. Okay. Yeah. I think it's overall declining a little bit. But the oxygen trends are kind of like overall it's declining, but there are areas where oxygen is increasing, and that has an effect on. So it's not like temperature where it's very simple; it goes up. Yeah.
Great, thank you very much.
Yep.
And our next speaker is Dawn Barlow.
Great. Well, thank you all for being here. I'm Dawn Barlow, and I'm from the Marine Mammal Institute at Oregon State University, and I'm excited to share some in-progress, ongoing work from my postdoc. And I'd like to acknowledge my co-authors on this work, Craig Strong and Dr. Lee Torres. So the study system of focus is the northern part of the California Current, which, as many of you know, is an important eastern boundary current upwelling system, bringing this rich, productive system to the coastal region. And in particular, we're focusing on the nearshore waters of the Northern California Current, which are further shaped by complex bathymetric features, including sloping, sandy bottom substrate, rocky reefs, kelp forests. It all create this rich mosaic of habitat for a number of species of conservation concern, including marine mammals. And despite its ecological and economic importance, the nearshore poses some pretty substantial challenges for systematic boat-based surveys. So it remains kind of a knowledge gap in that sense. Our study species of focus are these two nearshore marine mammals. And these are our two species of focus, but they have some important life history differences. Gray whales are migratory. They spend a feeding season feeding on epibenthic zooplankton prey, particularly around these rocky reef nearshore habitats, and they're in the region seasonally. Whereas harbor porpoises are resident to this area year-round, and our study area spans multiple breeding stocks. And they feed a bit higher up on the trophically on forage fish and squid. So our research objectives here are to examine the static and dynamic environmental drivers of distribution patterns of these two species, and to look at how those distribution patterns may have changed over time and consider potential implications with climate change. And we consider this, again, for these two different species with these key life history differences. And the way we're able to get at these questions is from a nearshore survey data set that was designed for monitoring marbled murrelets, a seabird species of conservation concern. And lucky for us, they've been doing these systematic nearshore transects since 1992, and these are within 5 kilometers of shore. And in addition to marbled murrelets, they've recorded other seabird and marine mammal species. So how this goes is the boat drives along a transect line. There's two trained observers on the port and starboard side. When they make an observation, they measure the distance to the track line, and also a handful of other things, importantly including that last bullet point, which is the observation conditions at the time. And that allows us to implement these density surface models. So as these observers are going along the track line, they're making observations under different conditions along their track line, as you can imagine. And so if they're looking for animals like this, really most of the time they're looking for more like that, which you can imagine will change under different conditions. So it's important here to account for detection probability. So to do this, we fit a detection function, which essentially accounts for the fact that fewer detections are made the further away you are from the track line, and we include different covariates to account for detections under different conditions, which allows us to estimate an effective strip width within which we can calculate density. And we implemented these in GAMs to estimate density for these species distribution models. So to start with gray whales, our main hypothesis here that I'll talk about today is that gray whale distribution patterns reflect these physical dynamics that influence nearshore retention. And I'll talk a little bit more about what we mean by that. Particularly, something we think might be important here is this upwelling relaxation. And so here we have a cross-section of our Northern California Current upwelling system, where longshore wind stress leads to this net displacement of water offshore, and that's replaced by this nutrient-rich deeper water through coastal upwelling. But when we get relaxation in that wind stress, that offshore transport is reduced, and we get nearshore retention of nutrients and potentially more aggregation of the important prey for these gray whales in the near shore. And so here we hypothesize that there's actually an important interactive effect between upwelling events and these relaxation events that will have some optimal conditions for the prey that these gray whales rely on. In addition, there are a number of other features throughout our study area that we think are important, again, for this retention dynamics, such as rocky reefs, headlands, and these areas where the inner shelf is a bit wider. So that's the 200-meter isobath line, and areas where that is farther from shore are these sort of recirculation areas that, again, influence retention. So let's look at our model results thus far, and I'll emphasize that this work is ongoing. So we ran these density surface models per region, and these are sort of these distinct bioregions of the California current. And for gray whales, there are very few sightings in that region 3, so we fit models for those more northern 2 regions. We include a number of different environmental covariates in these models and that offset to account for detection probability. And I'll highlight just a couple significant functional relationships that have come out of these models so far. In that region 1, we see this association with with hard bottom substrate, so indicating the importance of rocky reefs, where we know they feed in these kelp forests. And in that region 2, we see this association with headlands, particularly maybe an association with areas south of headlands. Across both regions, we see this pattern where higher density patterns at these sort of wider inner shelf areas. And then importantly, we see this significant interaction effect between cumulative upwelling and cumulative relaxation events, where there does seem to maybe be this optimal combination of the two. So as we think of the potential impacts of that climate change may have here, given these initial model results, one potential projection from recent synthesis work on what may happen to these eastern boundary current upwelling systems is the potential intensification of upwelling in poleward regions, or in other words, a spatial shift kind of northward in our case. And so if I pull this up again, looking at this interaction between upwelling and these relaxation events, what that's implying is that we may be headed for more this zone of that plot. And so if these gray whales are relying on these stable nearshore habitat features, these sort of static features, but in a changing environment that's headed to kind of a different part of that plot, there may be consequences for their foraging in the future. So shifting gears now to these guys, a bit smaller. With harbor porpoises, our hypothesis is that their distribution patterns are related to the distribution and interannual fluctuations of their prey. And a bit more specifically, we hypothesize that these prey association patterns differ regionally. They may be feeding on different things, different forage species in different parts of the Northern California current. And also that their prey association patterns may vary over time. So again, we ran these models with a number of different static and dynamic environmental covariates across these different regions. And I'll pull out just a couple of patterns here that came out as significant across all 3 regions, and that's an association with these shallower habitats and soft bottom substrate. Now, these models don't include prey at all, so we wanted to look at overlap with prey in a couple of different ways. We did this first by running a Williamson spatial overlap index, and that's a measure of spatial overlap between harbor porpoise predicted density and the predicted probability of a few of these really important forage species of the Northern California current. And these are from layers produced by Barmueling and colleagues. And then in a subsequent step, we included forage fish, some of these forage species in the harbor porpoise density models to see if that changed things. So looking at these spatial overlap patterns using that Williamson's index, to orient you here, that dashed line is at 1, and so when that dashed horizontal line, when these lines that represent overlap with each of these different prey species are above 1, that means a more higher association than due to random chance. And so we can see some interesting patterns emerging here over time. One is these regional differences in association between harbor porpoise and their prey. For example, that dark blue line representing association with anchovy is seen in the north, whereas further south we see more an association with mackerel and sardine. We also see some interesting patterns here with those sort of oscillating or flipping fluctuations in these association patterns, especially in that region 2, which could indicate potentially prey switching across different years. And we also see some changes over time. For example, this increasing association with these slightly warmer water species, mackerel and sardine, in region 2 since 2014. So then we included anchovy as sort of a representative colder water species, sardine as representative warmer water species in our harbor porpoise density models. Improved the models slightly, and we see some interesting patterns in the functional relationships that come out from those from these models that include prey. So in these columns, we have anchovy on the left, sardine on the right, and in that northern region, there's a significant relationship with anchovy, no relationship with sardine. That central region, we see no relationship with anchovy and this significant relationship with sardine. And in that region 3, we see a significant negative relationship with anchovy and then that significant relationship with sardine. So as we think about how climate change may play into this harbor porpoise story here, climate change may affect their prey through a number of different pathways, including through warming, habitat compression, nutrient supply, changes in phenology, or food web dynamics. And so there are sort of a number of different pathways that this may be playing out and continue to play out, and the question here is how will those impacts affect harbor porpoise distribution patterns? And we're still teasing this apart, or hoping to tease this apart. But what you can see here is annual predicted densities across our study area. And we do see these sort of stable hotspots over time, as well as some interannual fluctuation patterns. And if we look at this temporally, there are these interannual fluctuations in predicted abundance across all 3 regions. And sort of tying this all together, the implications from this and the overlap, prey overlap slide I showed earlier, is that they may have a few different avenues through which to respond to changes in their prey availability through either just distributional shifts or through prey switching. And that would imply that they have a bit of flexibility here in changing conditions, and at least they have showed some flexibility in the past, which of course begs the question, up to what point? And so with that, I'll wrap up there. I want to thank the Oregon Gray Whale License Plate Funds for supporting this research, also the many folks from Crescent Coastal Research that collected these data in the field, and Barb Muehling and Jack Barth for generally lending their expertise and feedback on this work. And with that, feel free to get in touch, ask any questions, and I welcome any feedback. Thank you.
Great, we do have time for a question.
Thanks, that was a really cool talk. I'm curious if you looked at any sort of like lower frequency, longer term sort of oceanographic indices or anything in your models. As we know, a lot changed in the California current in 2014, and I'm curious sort of like on a slower moving timescale, have you looked at any of those like larger oceanographic indices and effects on your distribution models?
Yeah, great question. The answer is yes, we've started to, and I didn't make it into the talk. But the way that we've looked at it so far is in more of a time series framework, which is separate from this distribution modeling approach. And there is a bit of a lagged relationship between PDO and harbor porpoises, not so much with the gray whales. It seems like that their response seems to be a bit decoupled from these broader, like ocean basin scale patterns that I would have expected to play a role, at least over a 31-year time series that we're looking at. So I think there's some nuances there that we still need to tease apart, and I would love to chat if you have ideas. Yeah.
Great, thank you. I think to stay on time, we'll keep moving, but thanks very much for your talk. So our next speaker today, and I think the last in this session, right, or this sub part of our session, is Raquel Ruiz-Díaz.
now? Yes. Awesome. Oh my God. Well, thank you for sticking here with me. My name is Raquel Ruiz, and I am a PhD student at the Marine Institute. And I'm going to show you some of the results I have for my PhD. They are still a work in progress, but it's about the response of snow crab to the ocean warming on the Grand Banks of Newfoundland. Well, climate change is one of the biggest challenges of our time, threatening species, ecosystems, and ecosystem services. We know that climate change is caused by the release of greenhouse gases into the atmosphere, which raise global temperature. The ocean is absorbing up to 90% of this heat, and this has led to an increase on the average temperature of around 0.8 degrees since the pre-industrial era. Ocean warming is altering the behavior of marine species, and it's making species to move polarwards by an average of 72 kilometers per decade, and also deeper into the water column. Although these changes really depends on the thermal tolerance of the species. Changes in the species distribution have an important implication for the fishing sector and also for fishing-dependent communities. The Grand Bank of Newfoundland is an oceanic plateau located off the coast of Newfoundland in eastern Canada, and is well known for its rich marine resources. This region used to be an important fishing ground for groundfish like Atlantic cod and flash fish. However, in the early 90s, most of this stock declines after a period of overfishing and also strong cold temperatures. At the same time, the biomass of invertebrates started to rise in this region. Currently, fisheries like snow crab and northern shrimp started to emerge. And currently, snow crab is the most valuable resource in the region, with a landed value of over 200 million Canadian dollars only in 2020. This region is really interesting since it has an inherent natural variability, with cold and warm periods fluctuated every 3-4 years. However, climate change is intensifying these periods and making the region to warm at a faster rate. The Grand Banks is a really interesting case study, since in this area, two water masses converge. The Labrador currents that bring fresh water to the banks, and the Gulf streams that brings water that are warmer and also poorer in nutrients. Here we can see a map of the temperature variability within the Grand Banks, and currently has been detected a retreat in the Labrador current as a consequence in a slowing down in the Atlantic meridional overturning circulation. And this is causing the Gulf Stream to shift northwards toward the Grand Banks. Therefore, further warming is expected in the region. So based on this evidence, and given the economic importance of snow crab to the economy of the province, I want to answer the following research questions. Is snow crab biomass and distribution changing in response to bottom temperature in the Grand Banks? And if so, how? And how will biomass and distribution of snow crab respond to future ocean warming in the region? So to answer these questions, I developed a spatio-temporal species distribution model, and I used 3 different types of data. So to fit the model, I used data coming from the bottom troll survey that is carried out in the region in spring and in fall. This bottom survey follows a stratified random sampling design, and it's done since, I use in a temporal series since 1996 to 2019, so 24 years of data, and I have more than 6,000 observations. For the predictions, I created a grid over the Grand Banks using R-INLA, and I used bottom temperature information from raster coming from DFO and bathymetry raster from the JEPCOP project. And finally, to forecast to the low and high emission scenarios, I used the BioOracle database, especially the bottom mean temperature, which is the average temperature from the period 2040 to 2050 from 3 different Earth system models. Regarding the model strategy, I developed this spatial distribution model with a delta gamma distribution to account for zero inflation in my database. Also, the covariates were added as a smoothing spline to account for non-linear relationships between our response variable and our covariates. And the temporal component was added as an autoregressive model of order 1 to account for correlation between years. And we create this model using the package SDMTMB and also with the help of R-INLA. And so my response variable is occurrence and biomass of snow crab, And again, the covariates are depth and bottom temperature. So getting into the results, we select our base model structure based on ICACI information criteria, but we also assess the relative importance of each covariate using the ICACI weight. So what we found is that our best model is the one that includes the spatial effect, depth, and temperature. However, when we look at the relative importance of these covariates, we found that spatial effects is the one that explains most of the variability in the model, followed by depth, and finally temperature. So when we extract the covariates effect, we found that the probability of occurrence and biomass of snow crabs both declines as temperature increases in the Grand Banks. And also, there is higher probability of occurrence at depths around 150 meters, whereas there is higher biomass and depths around 400 meters. And these results may be indicating these species have an ontogenic spatial distribution, with younger individuals living at slower depths and older individuals living at deeper depths. So that's maybe reflected in here. To understand how a species biomass has fluctuated over time, we calculated this index of biomass by summing up the densities calculated in our predictions and multiplying them for the cell area. But basically, what we can see here is the biomass of snow crab have declined over time, and it's currently in 2019 pretty low. This index of biomass, it's an improvement with the normal index of biomass that are usually used in some species. When you have like a stratified random sampling, usually you calculate an index of biomass using the swept area methods. And these swept area methods assumes that the species is homogeneously distributed within the strata, which is not totally accurate. So these results account for more spatial heterogeneity, and also because we do predictions over the Grand Banks, it can overcome sampling issues like incomplete sampling, basically, and also it accounts for covariance effects, like in this case, bottom temperature and depth. In terms of changes in the distribution of the species, we calculated the changes in the center of gravity, which is basically the location of the average weight of the population. And we can see the center of gravity has slightly moved toward the northwest of the Grand Banks. And finally, the last part of our study was to forecast the response of a snow crab to future ocean warming under high and low emission scenario. So here what we did was to create 4 different scenarios using 10-year average. So the past scenario is the average from 1996 to 2006. The present scenario is the average from 2009 to 2019. And then we have the low and high emission scenario be both the average from 2040 to 2050. And what we are observing here is the prediction for the delta gamma model, and it's in log scale, so we can observe better the differences in the distribution. But basically what we can see is that in the present and future scenario, there is a loss of biomass compared with the past scenario. In fact, the mean density in the Grand Banks used to be 2.5 kilograms per kilometer, whereas in the present scenario, it drops to 0.9, and further decline is expected in the future with values around 0.6. And no biggest differences were observed between the low and high emission scenario. And this is not really surprising because most of the difference are expected after the year 2050. But then regarding the hotspot location, and I think this is a really interesting thing that this model can tell you, it's where the hotspot location are whether they're going to change or not in the future. And we can see that our hotspot location remains in the same region, in the 3L division, and that we are going to lose, or it's expected to biomass losses are going to happen in the south of the Grand Banks. Now, how can we use this information to account for changes in the species? How can we use this information to inform management decision? It is important to adapt our management strategies to better achieve management objectives. So forecasting the future impact of ocean warming can provide valuable information to support strategic management advice. And when we talk about the strategic, we mean about the starting planning for long-term management actions. and support decision-making to better achieve conservation and exploitation objective. And also the use of spatial analysis offers the opportunity to implement spatial management strategies, and this allows, for example, to account for conflicts related with the use of the space. And I want to show you that this is really important in the case of the Grand Banks, since there is an overlap between the oil industry and the snow crab industry. And you can see in this map how the location for the exploration and exploitation of oil totally overlaps with the hotspot of the snow crab. And they have created a lot of tensions between both sectors, with fisheries claiming that snow crab fishery contribute more to the rural communities' economy. So basically, the results from this study can be used to start a conversation about the future of snow crab fishery in the Grand Banks and support decisions taken in this regard. And here I have some of the conclusions. Temperature and depth are drivers of snow crab distribution over the Grand Banks, although we acknowledge that there may be other drivers affecting this distribution, either biotic or abiotic. And snow crab is highly sensitive to ocean warming. The biggest biomass losses are expected to happen in the south of the Grand Banks. Hotspot locations remains in the same region over time, and this information is valuable to support management decisions. And that's all. Thank you.
Excellent, thank you. Do we have questions?
Thanks for the great talk. I was wondering, since it sounds like the intensification of the fishery coincided with your survey, if there could be a confounding effect of harvest on the partial effects that you detected, or if there's any way for you to account for this kind of highly spatialized catch effect on distribution and abundance.
Can you repeat your question again? Sorry.
Yeah, of course. So basically, it's about the effect of fishing during the time series on the trawl survey itself, and whether you modeled a fishing effect or whether you think that's influencing where you see abundance.
Yeah, we wanted to include the fishing effort into our model. The issue is that we don't have a high-resolution fishing effort that can be included. So we haven't, but a thing that we can do is to compare the hotspot location, because we know that fishers targets the hotspot area, and see whether these regions are like declining faster compared with the rest of the Grand Banks. But we cannot explicitly include it because this resolution issue. But yeah.
Questions?
Thanks for a great talk. I was just wondering if you have any ideas or hypotheses about what could cause this spatial, why is this spatial random effect, what is it capturing? Because you had depth and temperature, right, in the model? Yeah.
So basically the spatial effects explains variability that is not accounting for the covariate, so it's something that is not depth, it's not temperature. It may be related to, for instance, preference in the bottom, the substrate type. Yeah, it can be explaining, like, I don't know, some time of competition, like something that is not like I don't really know, but yeah, I mean, I think probably it's related with the bottom substrate.
Okay, yeah, that would make sense.
Yeah.
Thanks for again.
Thank you.
A final question? I thought there was one in the back there, yeah.
Thank you. I had the question, so in the projections from the US, are there any emerging species that you think will take over this southern niche of the crab?
Do you mean that there are other species coming from the US and occupying the space?
Yeah, do you know that? Because that could be a way to switch to another fisheries.
I don't know that. I really don't know if there is other species trying to occupy the same space of a snow crab right now. I don't know. For most study, they really find a a relationship between temperature and recruitment. So colder years benefits more the recruitment of the species. So I think that, yeah, most of the study point that temperature is really important, but I'm not sure about the difference occupancy in the space with new species. I don't know. Sorry.
Great. Thank you again to Raquel and to all of our speakers from this session. And we'll see you again after the break. And remember, there's break on that side, and there's also break over here. Thank you, Session 10, for sticking with us. We're going to get started again here. A couple reminders: if you're speaking, go up in the talk before yours to get your headset set up. And another point, so if you are a speaker, make sure you check out your Whova app, because people who are listening to the streaming version of this are sometimes asking questions, and it would be great if you could respond to those at some point after your talk. So make sure to keep an eye on that, so we can stay engaged with our virtual participants. Our next speaker here is Shahar Chaikin. Welcome.
Hi, everybody. So first of all, I'm very excited being here, and thank you all for coming. I would really appreciate your feedback after this talk, because this is a study in preparation. I also would like to thank, before I begin, to ECHO for funding my arrival to this place, so thanks. And let's begin. So today there's increasing evidence suggesting that warming coincides with forward range shift. Here is one famous, relatively famous example by Pinsky et al., showing the relationship between latitudinal shifts of 9 different marine assemblages against the change in bottom temperatures. And you can see the positive values in the y-axis will denote assemblages that move towards higher latitudes. And what they found across 360 marine taxa is a positive relationship, meaning that increasing bottom temperatures correlate with forward migration. And you can see here one interesting outlier in orange. That is the Gulf of Mexico that probably prevents the forward shift due to its semi-enclosed nature. We also know that warming coincides with abundance changes. Another interesting study by Hastings et al. Shows the relationship between abundance change and the spatial position of different populations. So values on the x-axis that above 0.5 denote forward populations. These are populations that are facing in the forward range of their range, and values below 0.5 are equatorial populations. And what they found in this study across more than 300 different marine taxa is a positive relationship, meaning that forward populations increase in abundance over time, while equatorial populations are actually declining. But what we're interested in this study is understanding, something just changed a bit, what about the range shift velocities? How do they relate into this story? And more precisely, is how does abundance relate to range shift velocities? And I'm asking this because we know that some species are slow shifters moving in rates of about 1 kilometer per year towards the poles, while others are quite fast shifters moving about 40 kilometers. In terrestrial environments, we can also find much faster shift rates as well. And we ask, do those slow shifters are prone to decline in abundance over time because perhaps they cannot keep up with pace of warming? And on the other side, do those warm shifters may find stable abundances or perhaps even increase in abundance over time because they can? And furthermore, we try to understand how does the spatial position relate to the entire story. Perhaps forward populations behave differently than equatorial populations. So to start examining these kind of questions, we constructed a simplified null hypothesis because we undergone many scenarios, and it was really complicated, and we tried to simplify things. And we have here, first of all, a range of hypothetical species, and you can see here its leading edge, which is the forwardmost edge of its range, and the trailing edge, which is the equatormost edge of its range, and some different populations. Each circle, it's a different populations, and it's The circle size corresponds to the population size, and in blue you can see powered populations, and in red those equator populations. So now we'll try to understand how does abundance relates to range shift velocities. So we might first have the range distribution of the species in T0 before the warming, and we can see that we have a unimodal curve according to the abundance center hypothesis for simplification. And we can see that the powered populations are smaller than those center populations, that most of individuals are within the center. So after a range shift, we may predict 3 different scenarios. The one will be that there is no range shift for the specific species, and the abundance will remain quite the same. The second scenario is a slow shift, meaning that the powered populations might increase in abundance with respect to the T0. Center populations should slightly decline, and equator populations might drastically decline. And this effect gets only stronger and stronger if we're talking about a fast shifter. So finally, if we summarize the relationship here, we have on the y-axis the population trends with positive values for populations that increase in abundance over time and negative for those that decline. And on the x-axis, we have the shift velocity. So powered populations, bless you, should increase in abundance. Center populations should slightly decline, and those equator populations might drastically decline and perhaps even extirpate from a specific region. Okay, so how can we examine this kind of hypothesis? We bind 2 global databases. The first database is called BioShifts, and it measured different climatic-induced shift velocities. And the second data set is called BioTime, and it measured abundance time series of different populations worldwide. So first of all, I would like to take this moment to thank those publishers of these databases that made it public and allowed us to explore this relationship. So thanks. And after combining these 2 databases, we end up with 2,572 different populations belonging to 146 marine fishes. And they were spread relatively worldwide. Most of them are in the North Atlantic, some in the Northeastern Pacific, other in Oceania, and some other sporadic populations. Great, so now we have the data, and we can examine the relationship between population trend, the slopes on the y-axis. This is the slope of abundance against time. And on the x-axis, the different shift velocities of the species in kilometers per year, and the positive values are for species that move towards higher latitudes, and negative values for those that move towards lower latitudes. And what we found was actually a negative, significant negative relationship, quite the opposite than we thought, because those fast powered shifters are actually declining. And we thought that those fast shifters should perhaps sustain their abundances, or perhaps even increase because they are fast shifters. So I guess as most macroecologists, the next step will be to conduct many sensitivity analysis and check the robustness of this pattern. And first of all, we thought that this pattern might be driven due to those extreme shift velocities. So as a first stage, we removed those extreme shifts. We ran the analysis, and we found out that it's still significant and negative, and the slope became even a bit more negative. So we find no evidence that this relationship is driven due to those extreme shifts. Next up, we know that some species in our data set are represented by many populations, while others are represented by only a few populations. So it also could be that the patterns are driven by those species with many populations, and thus we cannot really generalize what we find. So what we've done here, we averaged the population trends by species and reran the analysis at the species level. So on the y-axis is the mean population trends for each species, and what we found is still a significant negative relationship. So given this data, we find that this pattern is relatively robust. As a next stage, we wanted to understand how does different populations respond to this relationship. So this is where we add the spatial position. So positive values are for populations that were sampled in the forward side of the range, and negative values for those that were sampled in the equator side of the range. And I just would like to note here that we do not have, our data is not represented mostly by those populations at the extreme leading edge or the extreme equator edge, and it's important because I guess all of us expect that at the extreme leading edge, we will find colonization and populations should increase, but we do not investigate these regions. Most of our populations are within the known species range. So just a small note. And the next step we've done is running interaction between shift velocity and spatial position. And what we found was a significant interaction, meaning in this case, you can see in red those equator populations that are relatively stable, not really matter what is the shift velocity of the species. And that was also counterintuitive to us because we thought that those equator populations that are also in the warm edge of the range might decline due to perhaps adverse warming. But we see a stable trend. And we thought that perhaps it could be related to climatic depth. So we cannot really assume that those equator populations are fine and they are persisting and it's great. We still, in my eyes, need to keep monitoring those populations. And we also know from different studies that climatic depths are indeed something that we find support of in marine fish. Polar populations are those that decline with increasing shift velocities, and that's come in accordance to the main pattern that I just shown you before. It could be driven by those polar populations. And if I come back to our hypothesis, and we said that we have an abundance center, we work up according to the abundance center theory, we actually might find, if we imply our results, we find that the abundance center hypothesis might not work in this case. It could be more of a forward-skewed distribution. And indeed, there's a kind of a great bulk of literature suggesting that the abundance center hypothesis, in many cases, doesn't really work. Another analysis, the final analysis that I'll show here, examines the relationship of different commercial status. So we know that fisheries may impact population trends, and we categorize the species to low and high commercial values, and we run a three-way interaction term between shift velocity, spatial position, and the commercial status, and we find a non-significant interaction, meaning that the relationship of population trends on shift velocity and spatial position, we have no evidence that it changes according to the commercial status of the species. We can see, for example, that polar populations are declining no matter to the commercial status. And I don't have time to show further analysis, but I can discuss it later. But we also investigated the vulnerability of different species to fishing. But I would be happy to talk about it a bit more later. So to summarize it up, marine species track climate much faster than terrestrial species. We have many studies that showing these patterns, but I think one of the main messages of this study is that being a fast shifter doesn't mean that you're a climatic winner. And I think it's something that we need to keep investigating. It could be that those fast shifters are actually climatic losers. And if we try to give a more applicable message here, then range shift velocities can inform the conservation of local populations. For instance, if you are a marine protected area manager or if you are a fish stock manager, of course you need to know which species you have in your range, but not only that, you may also need to understand what do we know about the range shift velocities of those species? What do we know about the population, the spatial position of those populations? And it might have a great meaning. And polar populations might require special attention. So thank you very much for listening. If you have any questions, I'd be happy to answer them.
Thank you. We have time for a question.
So I was just wondering if you've looked at all at, for some of the species, like potential habitat or suitability indexes, because I've seen for a much smaller number of species, the ones that are shifting their range the most are also the ones with the largest declines in potential suitable habitat. So I'm like thinking, like, could that be a pattern that you're seeing also with the declines in abundance in your data set?
Are you talking if I have patterns of how habitats are changing?
Yeah, or like habitat suitability, is it declining more rapidly for the shifting species, or is it changing a way where it relates
I also
to?
looked at the thermal ranges of those species, so to understand if they're located in the warm edge or cold edges. The results are quite similar to what I've shown in the spatial position, so I didn't repeat them, but I have it here. So in this case, we didn't find any, it came in accordance with our main findings. But if you have another suggestions for how I can investigate the habitat suitability, I would be happy to do so. Yeah, and I also observed the minimum depth of each species to understand if we see differential responses, but I don't have the concrete, like the observed data of these species, so it was more like a fish-based data, so I neglected it. But I'm open to suggestions, of course.
Thank you. I'll see if there's time for more questions.
Thank you.
Great. I think we're actually out of time now. Do just have an announcement that the speaker that we missed at the very beginning of the session, Sheku Sei, has actually arrived now, and so we will have that talk at the end at, let me look at the time here, that'll be at 5 o'clock, and so the session will end at 5:15 or 17:15. Thank you.
Thank you.
Welcome to our next speaker, who is Zoë Kitchel. Thank you.
Thank you all so much for being here today, and I want to say a special thank you especially to the conference hosts for just such a fantastic and dynamic program thus far, and I'm really looking forward to the rest of the week with you all. My name is Zoë Kitchel, and I'm a graduate student at Rutgers University, which is in New Jersey in the States. Despite the fact that the title of this session is Beyond Species on the Move, I would like to begin by reminding you all that species are indeed on the move. And I think what we've learned from today is that the way in which species move to new spaces is an extremely complex and dynamic process that incorporates direct effects of their abiotic habitats and also really complex indirect effects at times from the more biotic habitat characteristics. And it's especially exciting to look at species range shifts in the ocean because, as our last presenter was saying, species range shifts in the ocean seem to be happening much faster than those on land on average. And there are a lot of reasons why that happens. Part of it is because our marine critter cousins are extremely picky and very sensitive to temperature and other types of conditions in their environment because, in general, they haven't adapted to variability because the ocean, compared to air, is much better at maintaining over days, weeks, and years. And then also, in general, there are fewer biogeographic barriers in the ocean as these critters move to new spaces. That being said, there are some really interesting ways in which the environment within the ocean is constraining how species move around. And today I'm going to be focusing on continental shelf species, many of which have been highlighted today, from plankton to kelp and seagrass and whales and dolphins. So many species that we're really interested in the ocean habitat are highly dependent on these extremely productive, unique habitats. But what's really interesting about continental shelves is that they're not distributed uniformly across the globe. There are some areas where the continental shelf expands hundreds of kilometers from the shore, but there are other areas where they're quite narrow, only spanning 1 or 2 kilometers. This presents the question of, as species move deeper and they move to higher latitudes, are there situations in which continental shelf itself is going to be a first-order constraint on their ability to shift? This isn't the first time that species have had to deal with this limitation in continental shelf area. If we zoom back in time to the late Ordovician, around 450 million years ago, there was a quite catastrophic extinction event many of you are probably familiar with, where we lost 85% of critters in the ocean. And a number of researchers think that at least part of the explanation for this loss of species in response to a significant change in climatic conditions is because there wasn't this latitudinal corridor for species to take advantage of because of the arrangements of the continents, because they were so different than the arrangement of the continents more recently. But if we fast forward to a similar period of climate intense variability, more recently, in the late Cenozoic period, we had a continental arrangement that was very similar to what we have now. Species were able to take advantage of these corridors. And so again, researchers think that at least part of the reason that we didn't experience a mass extinction during this period is the fact that species were able to take advantage of these corridors to find more suitable habitat space. So this inspired us to ask the question of, today, what does the distribution of shelf area look like, and what might that mean for species trying to move to deeper depths and also to new latitudes? First, we looked at habitat area by depth, specifically across all of the large marine ecosystems that were not in polar regions. And we used eTopo1 to extract the bathymetry data, the depth information, from these different large marine ecosystems. And here, just to show you one example, we're going to focus on the Norwegian Sea because it seemed relevant. And what we did is we made these really beautiful hypsometric graphs where we looked at the distribution of area across depths. We used some really awesome techniques developed by Elson and Tingley in 2015, where they were looking at this same story, but in terrestrial mountain ranges, in order to classify these different hypsometric curves into a few different categories, which might help us understand what types of changes species are going to face in habitat. So to show a few more examples, starting with the Gulf of California, this is a distribution of area across depths that fit into our shallow dominant distribution. If we move to Norwegian Sea, the fan favorite, we see more of a multimodal distribution in area over depths. And if you move all the way to the right, you see the Benguela Current, where we had a mid-dominant distribution in depths, in area across depths. We also looked to see if there are any examples of a deep dominant distribution, but we did not find any. Good news. When we look at the overall picture of all the large marine ecosystems that we looked at, again, kind of like positive, exciting news is that in general, most of the large marine ecosystems exhibit these multimodal distributions in shelf area across depths, which means that there might be a period where an organism is shifting deeper, that it might actually have an opportunity to expand its population, or maybe the number of species will actually increase that area can support. We also asked a similar question, but in the context of latitudinal shifts, using similar techniques. And what we did is we binned all latitudes into 2-degree bands, which is approximately representative of an average shift of a marine species over the course of 40 years. And then we summed the area available on the continental shelf for each of those bins. That information is captured in this black line across this latitudinally oriented graph, and then just the overall trend is shown in gray. We also highlighted areas that experienced significant contractions in shelf area, which are shown here in purple, or significant expansions, which are shown here in orange. And we then did that for all of the contiguous coastlines across the world. And I won't spend too much time here, but I just wanted to point out that what really stood out to us is just the regional variability, both in terms of which hemisphere you're in. The northern hemisphere are the upper pie charts, and the southern hemisphere are the lower pie charts, which ocean basin you're in, and then also whether you're on the east or the western side of that ocean basin. The pie charts show the relative number of significant contractions and significant expansions. So the fact that there's so much variability in the amount of shelf area available to critters as they're moving deeper and higher in latitude begged the question of how might this impact the number of species that these different habitats can support. So we continued our analyses inspired by the species-area relationship, where we know that the number of species that an area can support depends on the size of that area. And specifically, we used a power law that's been developed for marine fish, because I'm a marine fish person and I'm biased, but you could use similar methods for a range of other taxa on the continental shelves. And so we expanded what we did, taking the changes in shelf area and translating that into what it might mean for the change in the number of species that these different latitudes or different depths can support. So here's what we found, again, focusing on the Eastern Atlantic, where we are today, and the latitudes where we might be more likely to see a loss of species are highlighted in purple, and those areas where we are more likely to find a possible increase in species are highlighted in orange. We did the same thing for our hypsometric curves, looking at depths across a wide range of diverse large marine ecosystems. And again, this helped us identify depths where you might possibly see an increase in species or a loss of species, depending on the shelf area that's available. Again, we did this for all the areas that we could and had bathymetric data for. And I just wanted to highlight a few interesting regions where we might expect to see these increases or declines in species richness. Specifically, the northern hemisphere, because the shelves tend to be a nice passageway to the Arctic Ocean, and also because the shelves tend to be so wide, we did see a number of instances at those latitudes where we might expect to see an increase in richness. In contrast, if you look at the shelf area of the Northeast US large marine ecosystem, and then also the Southern West Pacific, as species move deeper and higher in latitude, we might expect to see a decline in the number of species within those communities as they move. So in conclusion, the good news is that it seems like most large marine ecosystems exhibit this multimodal depth distribution, which means that there are opportunities for populations and communities to expand as they move deeper. Also, there is higher shelf habitat availability in the northern hemisphere and compared to the southern hemisphere because of those wide shelves that I just talked about, and also because there is not an easy way to get from the southern tips of South America and Africa to Antarctica. There are opportunities for expansion and the threat of contractions, and they are largely shaped by regional bathymetry. And I think an exciting extension of this would be to look at a more local scale where you could use a higher resolution of bathymetry data to see how more like nuanced bathymetry might play into this. And then specifically, we just wanted to point out that these regions that we've identified as contracting might be good locations for conservation and management efforts, while in contrast, these areas of habitat expansion might actually serve as refuges moving forward. Huge thank you to my co-authors, Becca Selden, who is here today, Haley Conrad, who I want to highlight was an undergrad on this project, Malin Pinsky, the whole Global Change Ecology Lab at Rutgers, my funding sources, and especially to University of Maryland and Hui for making it possible for me to be here today. Thank you so much.
We have time for questions.
This was awesome, thank you. I was thinking about your use of the species area curve because that sort of assumes equilibrium. It's like how many species you have after competition and other things take its toll. Do you think that means that even in these pinch points where you have less habitat, they could potentially be migration corridors so long as there's any habitat in a non-equilibrium future?
I think it's a really good question. We didn't take into consideration time at all in any, these are very speculative analyses. And I think the period of time in which species like have to coexist plays a big role in this. And I think it's going to depend a lot on what type of species you are. If you're a species that really relies on like benthic habitat and you don't move a lot, I think competition is going to end up playing a much bigger role and maybe impacting the amount of species that can persist there in comparison to like a very highly migratory species that might just like zoom through and find a better space.
Another question. Don't be shy. We have a minute.
You're also welcome to take time, reflect, find me at another time.
Yeah, I was going to ask whether you had some data, seasonal variation data, and what the experience was during your studies here.
Yeah, really good point. We were more setting the scene for the possibilities that could arise, and so we didn't really look at any temporal variation. But I think it's a really interesting question in terms of, as I said before, species range shifts are so dynamic, and seasonality and the way that species interact with habitats differently over the course of the year is definitely going to play a part in their ability to take advantage of these habitats. Thank you. Thank you so much.
Great, thank you very much for talking. And our next speaker in this session is Laura Gruenburg. Did I get that right?
Okay, cool. Hi, everybody. I'm Laura Gruenburg. I'm a postdoc at Stony Brook University in the United States. And today I'm going to talk about climate velocity in the vertical dimension and how it can help us learn a little bit more about species range shifts. And first, I just want to acknowledge my co-authors, Janet Nye and Leslie Thorne. Were also presenters in this session earlier, so I hope you all saw their talks. And then Kamazima Louisa also. So first, I just want you to take a look at this graph that I have in the background on our very first slide. It's just showing our global average mean temperature. It's increasing over about the last 100 years in this graph. Should come as no surprise to anybody here. And it's increasing a lot over the oceans, also not a surprise. So here we're looking at sea surface temperature in the northeast United States. And we had some talks earlier that talked about how in the Gulf of Maine, temperatures are increasing really rapidly. We're also seeing increases in southern New England and the mid-Atlantic bight. And especially for this session, when we think about this warming in the ocean, we want to know, what does that mean for marine ecosystems? And what does it mean for individual species? The last two talks really set this up quite well. Where are these species going to move? Where can they find suitable thermal habitat? And how fast are they going to shift to these new places? So one tool that we can use to learn about these species range shifts is climate velocity. And it's defined as the instantaneous local velocity along Earth's surface needed to maintain constant temperatures. So what does that mean? Well, we can imagine all of us in this room, say we are species session 10, day 2, and it's 55 degrees-ish outside. So if we wanted to maintain that thermal habitat, how fast would we have to walk and in what direction in order to maintain that? So we can determine this using gridded temperature data, and we calculate it by dividing long-term temperature trends by time mean spatial gradients of temperature to get us a velocity. So early studies looked at this mostly on land, and we can see here the climate velocity on each one of the continents, with blue being pretty low speeds in kilometers per year, and red being really, really high speeds. And you can see some patterns start to emerge. For example, in places where there's steep topography, like here in Norway, we tend to have really, really low speeds. And that's kind of analogous to what we're going to see in the ocean, so I just want you to keep it in mind. So in addition to these studies on land, there have been many studies looking at climate velocity in the ocean, although they mostly focus just using horizontal climate velocity at the sea surface. In one of those studies, we actually heard about 2 hours ago from Leslie Thorne. I'm just going to summarize it real quick for those of you who may not have been here. So she looked at horizontal climate velocity using sea surface temperature in the northeast US, and then compared that to the actual movements of a couple different species. So pilot whales and Atlantic mackerel, which did seem to move northward. And then some other species, especially the long fin and short fin squid, did not move northward as we would expect with the horizontal climate velocity. And instead, they moved deeper. So this got us all thinking, maybe the horizontal climate velocity is not enough because it's missing this vertical dimension. So that's when we decided to calculate climate velocity just in that vertical dimension. And instead of using sea surface temperature, then we need a 3D gridded temperature data. And so for this study, we used the GLORIES 12 reanalysis dataset. We like this one because it's global, so we're able to compare between different regions. And it's relatively fine scale as far as global reanalysis goes, at a 1/12 of a degree. And we're looking at data from 1993 through 2020. We also focused on the large marine ecosystems, as the previous talk did as well. These are really important, especially for human populations. About 80% of total fisheries catch happens in these large marine ecosystems. And we've also chosen to focus on the upper ocean. So we're just looking at the upper 200 meters. So we made our calculation very, very similarly to the way they do in the horizontal. First, looking at the temperature trends at each one of our grid cells, and then at the spatial gradients. But instead of looking at horizontal spatial gradient, we just looked at the vertical spatial gradient. And then finally, we just did that simple division, dividing the temperature trends by the spatial gradients and giving us our velocity. So in addition to the vertical climate velocity, we also calculated the horizontal climate velocity at the surface in each LME, just so we had something to compare it to. And I'm showing here the two components of the climate velocity. So on the top is our temperature trend, and on the bottom is our time mean spatial gradient of temperature. So to start with, on the top, on the left-hand side, is the subsurface temperature trend. So the temperature trend at every single grid cell that is in between 0 meters and 200 meters. And on the right-hand side is the surface temperature trend, so just at the surface bin. And red colors indicate warming, blue colors indicate cooling. Also, probably not a big surprise that there's a lot of warming, although there are some regions where there's a very slight cooling. And then on the bottom is our second component, which is the time mean spatial gradient. Left-hand side shows the vertical temperature gradient. Here we have a lot of negative values in brown. That just means as you go deeper in the water column, it gets colder. Although there are some regions where as you go deeper, it gets a little bit warmer, and we're going to return to that a little later. And then on your right-hand side is the temperature gradient for our surface bin. And all these values are positive because of the way that we calculated this. It's consistent with previous studies. So our final horizontal climate velocity, the sign of it, negative or positive, will just be based on the sign of the temperature trend. So here we're looking at the climate velocity. On the left is the vertical climate velocity. On the right is the horizontal. And the first thing I want you to note from these two graphs is just the difference in the units. So horizontal is kilometers per year, vertical is in meters per year. So that's a pretty big difference. In the vertical, these purple lines show negative climate velocity. That means that the isotherms are deepening over time. And that represents most of our grid points. About 78% of them showed this deepening over time. And our peak is actually really, really close to 0. About 49% of all of our grid points were between -1 and 0 meters per year. So that's a deepening, but it's not super fast. And that's in comparison with our horizontal climate velocity, where we have peak values, say, at about 8 kilometers per year. So you can imagine if you were some species, would you rather move forward 8 kilometers per year, or maybe just move deeper, like half a meter per year? So it's definitely something to think about when we consider species range shifts. Next, what we did was we looked at every single LME individually. Clearly, we don't have the entire rest of the week to talk about this, so we'll have to move on from that. But there were a couple of trends across some of these regions that I wanted to highlight for you all. So in tropical regions, especially in the horizontal, we had really, really large horizontal climate velocities, generally due to the pretty small spatial gradients that we saw here. In temperate regions, we had smaller horizontal climate velocities due to larger spatial gradients. We also started to see some regions that had a bimodal distribution in the vertical climate velocity due to some salinity dominating the stratification. And then when we move on to polar regions, that bimodal distribution becomes pretty evident. Once again, many of these regions have some stratification that's salinity dominated instead of temperature dominated. So here we're looking at all of the LMEs, and we're summarizing it by looking at median horizontal climate velocity and median vertical climate velocity. So purple colors show negative median vertical climate velocity. Green colors show positive median vertical climate velocity. And the strength of the shading indicates whether it was low, medium, or high in terms of the horizontal climate velocity. And there's some broad trends here that's pretty similar to what I just said in the last couple of slides, but in the tropics and subtropics, we tend to have higher horizontal climate velocity, but also negative vertical climate velocity. This could become important in places where the organisms might not be able to move further north, such as the Bay of Bengal, or perhaps in the Indonesian seas, the Sulu-Celebes Sea. When we go further north and south, we get western boundary current regions that have lower horizontal climate velocity and a negative vertical climate velocity. Eastern boundary currents also show those same horizontal and vertical climate velocity trends. And then there are some regions where we have positive vertical climate velocity, and those just tend to be where salinity stratification is dominant. So we might have a relatively fresh but very cold layer on top of a slightly warmer but very, very salty layer. And we wanted then to compare this to the biology. Of course, it'd be great if we could have bottom trawl data in all of those LMEs, but of course we do not. So we started with the Northeast US, and we looked at the 58 most common species there. And so each one of these plots is looking at a box plot of the vertical climate velocity, and then these little blue diamonds are showing if there was a statistically significant deepening trend for each one of these species. So on the top left, we're looking at species that moved farther northward than what their horizontal climate velocity would predict, and we're seeing that 2 of them also deepened. On the top right, species that moved less northward than we would expect, 5 of them still deepened. Bottom left, species that moved just as we would expect to the north, 2 of them still deepened. And then when we looked at all the rest of the species, the ones that showed no significant north-south movement, 12 of them still showed a deepening trend. So the big takeaway from this slide is that we just really can't ignore the vertical dimension here. Even if our species are moving as expected, they still might be showing a deepening. I don't think I quite have time to discuss that, so I will leave you with these key points. Climate velocity in the vertical is on the order of meters per year and is generally negative. Spatial gradients play a really big role in determining the relative magnitude of climate velocity. And significant deepening is seen across multiple species, those that shifted north and those that did not. So we really need to include the vertical dimension when we're talking about species range shifts. And thank you.
Thank you. We have time for questions. I see one in the back here.
Thanks for a great talk. I have a question about the sort of vertical resolution of your 3D data. So you said it's 1/12 on the horizontal.
Correct, yeah. And then in the vertical, it's the resolution is varying in space in the vertical. So at the surface, it's very fine scale, and then the scale gets more coarse as you go deeper. So
We ended up doing a 5-meter linear interpolation down to 200 meters in order so that the bins in depth would be consistent throughout the water column.
Yeah.
Yeah, it's not perfect, but...
I'm just wondering if like that sort of extra resolution can add like heterogeneity, which would reduce the velocity? Or...
You mean like in regions that are very well mixed, we end up with like a lot of bins that have kind of like very little temperature gradient? Is that what you...
No, I think more, but I don't know. Maybe I'm misunderstanding. We can talk later, I think.
Okay, yeah.
If you want, yeah.
That's good. Yeah.
Time for one more short question, please.
Yeah, it's very short. I would like to know if you're using, maybe you have mentioned it, gradient-based velocity or distance-based velocity?
Gradient-based, yeah.
Great, thank you. I'm also interested. Maybe there are some people here working on climate velocity, and we have David Skuman, so maybe we can gather.
Great. Thank you very much to our speaker. Our next two talks are going to be presented, well, they are going to be pre-recorded videos. They could not attend in person. So our next one is from Julia Polo, and I think that they will get that queued up in the back for us. Thank you.
Hello, everyone. I am Julia Polo, PhD candidate at Spanish Oceanography Institute in Spain. First of all, thanks everyone for your presentations and ECCWO organizers for making this great conference happen. I'm going to show you an ongoing study I am carrying with some colleagues from Spanish Oceanography Institute and Tromsø University on the interacting effects of fishing and climate change on life history functional traits of marine species. Sorry. Okay, some of you may already have some experience with traits, with life history or functional traits, as they are known. Traits or species attributes are often used in ecology studies instead of the more typical taxonomy-based study to assess the state of species or populations and even wider assemblages, reaching the ecosystem level. Examples of these kinds of studies are the IPCC-inspired climate change vulnerability assessments, or the creation of indices of sensitivity to a certain pressure, such as fishing, pollution, or climate change-related stressors. All these trait-based assessments usually focus on the response of a particular species trait to a particular driver. An example of this is the expected tendency of assemblages to shrink in maximum size or turn towards faster life cycles when heavy warming or heavy fishing take place. Body size and other traits such as fecundity or trophic level are expected to respond to external pressures and are often used in risk assessments. Now, what happens is that many of these researches rely on expert judgment, meaning that they assume that species adapt to stressors in many ways by either changing their phenology or their distribution, but also through population and wide community responses. And the direction of this response of the trait to the stressor is often an assumption that might be relevant in terms of management and often relies on expert judgment. So another thing is that stressors can not only act additively on communities, but they can also interact, sometimes affecting the resilience of the system and modulating the response of the community. And also in trait-based
studies, it should be taken into account that a trait might respond contrastingly to different pressures. So we might only be taking into account the expected response of a trait to a certain pressure, and if that trait in our study system does not respond as expected, we might be interpreting wrong what is happening really to that system. So that's why in our study, before using traits for the assessment of systems and ecosystems vulnerability, we have aimed to assess whether the response of a trait to a stressor can be different depending on the community or the environment of the species. And therefore, if before going into the design of a trait-based index, it would be best to first analyze the response of the traits to the stressors of interest in that particular community. Also, in the modeling of the traits response to warming and fishing, we have looked at possible interactions between the stressors. And we have simply done this by modeling the response of a selection of typically used life history traits to warming, represented as sea surface temperature, fishing through VMS data, and to their interaction. See if there was some level of interaction, and if pressures were synergistic, antagonistic, or how traits were responding to this combined effect. We have modeled the traits response to warming and fishing with data from 2 marine communities with different degrees of exposure to climate change and fishing. One in an area in eastern North Atlantic, Cantabrian Sea in the north of Spain, and another one in the eastern Mediterranean Sea. We have used abundance and trade data for the communities associated to these 2 regions from 2 scientific bottom-up surveys, from which we selected the most representative 250 vertebrate and invertebrate species, and then collected from bibliography, from literature, the most commonly used traits, which we consider were responsive to fishing and warming. Here you can see this different exposure of both communities to the stressors. You can see to which ranges of fishing effort in the y-axis and temperature in the x-axis the 2 regions are exposed. The data of Cantabrian Sea at the left are generally located at a much lower temperature range than the Mediterranean at the right. We have used generalized linear models on a selection of traits on longevity, body size, fecundity, offspring size, growth rate, age at maturity, and spawning. Spawning being the number of months a species can spawn across the year. And we have explored through these GLMs, through these models, the direction of the response of these traits to fishing, to climate, and to their interaction. As you can see here, we have also modeled the response to the lagged pressures, combining temperature and fishing with 0, 1, 2, and 3 years of lag. As a result, we would have for each trait a total of 16 models with the different combinations of lagged stressors. We included the lags in order to see if the direction of the trait response to the pressures and their interaction was coherent through the different models. For example, if longevity was responding positively to temperature, positively to fishing pressure, and positively to their interaction through the different combinations of lags, meaning through the 16 models. And this is what we got. These box plots summarize the direction of the significative slopes of each trait. Of each trait's response in the x-axis are located the traits to temperature in this case. The box plots are the upper side of the plots are traits that have a positive response, and those in the lower side
of the plot have a negative response. Cantabrian communities models are in red and Mediterranean in blue. Age and maturity, for example, had 14 significative models in the Cantabrian region. This is the first box plot to the left, but no significant models in the Mediterranean, unlike body size at the bottom in blue, which only had 5 significant models in the Mediterranean region and had a negative response, the temperature in this case. The fact that almost every model for age and maturity gave a positive response, 14 models out of 16, gives us some confidence on the response of the trait. Here are the traits' responses to fishing. As you can see, longevity has opposite responses in Cantabrian and Mediterranean regions. Every model in the Cantabrian community was significant, represented by this little number in black, 16, while only 3 were significant for the Mediterranean region. And these are the slopes of the model response of the traits to the interaction among fishing and warming. In general, although for some of the traits there seemed to be a synergistic effect between the two pressure, being a positive response, the upper side of the plot, the effect of the interaction on the trait responses is very low, with values that surround 0, except for longevity, for which it is slightly larger in Cantabrian region, but as you can see, it doesn't really have a big effect. The fact that 15 out of 16 models had a significant positive slope gives us certain confidence on the larger effect of the interaction on longevity. So to briefly summarize our findings, we have seen some traits respond as expected, respecting the response to fishing. The models in the middle, here you have the 3 blocks of box plots to the right, and the models in the middle represent the trait response to fishing. At higher levels of fishing effort, the communities tend to foster life strategies, while some traits respond in the opposite direction to the one suggested by literature, the one expected, as is the case of age at maturity and offspring size, which one would expect would decrease with temperature, but in the Atlantic region, in Cantabrian Sea, shows the opposite effects. We've also found traits that respond differently depending on the community, such as offspring size to warming, which increases with temperature in the Atlantic, or the trait longevity, for which the interaction of warming and fishing has a modulating effect on the response. We did find a significant effect of the interaction in general, mostly for the Atlantic region, but note that in every model, the effect of the interaction was very low. And thus, in communities with different interaction landscapes, such as these 2 we have worked with, primarily due to their different thermal regimes, we can say the design of vulnerability indices based on traits needs to account for regional differences in trait responses to stressors. The interaction between stressors can modulate the community's response, and these kind of regional local approaches to ecological mechanisms can support efficient management actions that would avoid maladaptation. Here, our main take-home message: climate change and fishing impacts on marine species traits are context-dependent and potentially interactive. Thanks a lot. Please contact me with any questions or suggestions.
Thank you. We'll just wait 2 minutes to start our next talk. And a reminder that we will have the talk that we missed earlier, we will have at 5 o'clock. So please stick around for an additional talk after this one. If you have questions regarding this talk, please do email the speaker. You may also talk to Manuel Hidalgo, who's over here in the corner. Okay, my clock says it's time. So our next speaker will also be a recorded talk, and this is from Dawit Yemane. Thank you.
I'll be presenting you today the result of the work that I did with my colleagues on change in species distribution and biodiversity pattern in response to projected climate change of South Africa. Starting with the objective of the talk, the main objective of the talk is to assess the potential effects of climate change on species distribution and hence biodiversity. That will be looking at species-specific climate change impact on their distribution and community-wide change in distribution as a result of climate change and climate-driven long-term change in biodiversity. And doing that also to show the potential use of openly available occurrence records and environmental data from remote sensing and generating useful products. This study will be focused on ocean of Southern Africa, but mainly based on data within the EEZ of South Africa. Species distribution in the marine environment, the distribution of various taxonomic groups is known to be regulated by the environmental variables. And we also know long-term warming in high latitude region has been associated with corresponding biological change. This will be including distributional shift, mostly forward shift, but also vertically deepening, and shift in phenology, with a potential ecological implication, in some cases commercial implication for target fish stocks, and change in biodiversity. Biodiversity maps are relevant for identifying the priority area of conservation as an input in marine spatial planning and area-based management, and to provide baseline state and identify spatial and temporal dynamics in biodiversity. As we all know, globally there is an increasing impact on the marine environment coming from increasing demand for and competing use of marine resources, habitat degradation, and local extinction compromising ecosystem goods and services. And world population globally is projected to grow, and climate is also projected to change substantially. Thus, it's important to study the potential effects of climate change on species distribution and biodiversity patterns. Generating biodiversity maps. Biodiversity maps can be generated in multiple ways. The easiest and the first one will be identification of occurrence point of species by spatial grid cells, but this can be a bit patchy because there is no complete data for all spatial grids.
And the second will be prediction from macroecological models. The third will be stacking of individual species distribution maps that will be taking advantage of readily available occurrence data and environmental layers from remote sensing to generate distribution maps, and then stacking them to construct biodiversity maps. In the context of this study, data sources are described below, starting with the occurrence records. The occurrence data for all taxonomic groups considered in this study were extracted from ORBIS. These records were split into three major functional groups: fishes that will be comprising tailless, chondrichthyes, and cephalopods, zooplanktons, and benthos. And all of these records were limited or cropped to the boundary of South Africa. Coming to environmental data, all of the environmental variables used to model the distribution of species considered in this study were extracted from BioOracle. Currently, BioOracle comprises about 99 geophysical, biotic, and climate layers. Also, for some of these variables, they are available at three temporal windows: the contemporary, as the present period, and middle of the century 2040-2050, end of the century 2090-2100, and the four emission scenarios or climate change scenarios from the low emission scenario RCP 2.6 and high emission scenario RCP 8.5. These environmental layers were also cropped to the EEZ of countries in Southern Africa. Our species distribution modeling. An ensemble species distribution approach was considered to model the distribution of all species, and a total of 174 fish species were considered, 4 species of zooplankton, and 31 species of benthos. 6 correlative statistical models were considered in this study to construct an ensemble distribution map. These are the classification tree analysis, random forest, multivariate adaptive regression spline, support vector machine, generalized linear model, and artificial neural network. Inclusion of model into the ensembles were performed. They were based on their predictive performance, and the measure of performance used as the measure of performance used for each model was the AUC of the model. Generating biodiversity maps by stacking based on maps of distribution of multiple species richness or biodiversity maps can be generated in multiple ways. First one is stacking binaries of the predicted probable presence absence. These tend to result in overestimation of local species richness. The second will be stacking probabilities, that will be stacking the predicted probability of occurrence. These also tend to result in overestimation locally. The third will be a calibration approach, where a regression method is used to calibrate the prediction from either stacking binaries or stacking probabilities. In this case, the probability of occurrence of a species in a site will be calibrated based on a regression model of observed richness for a grid cell and predicted richness for a grid cell. So this is a project flow chart or the model pipeline to construct biodiversity maps, starting with data preparation for the occurrence records, and also preparation of the environmental layers, and then constructing a species distribution model, and for which partial effects are generated and relative importance are generated for each species, and also ensemble distribution map, after which are stacked to construct species richness by stacking. Coming to the results, for some of the species from each of the 3 functional groups, the predicted maps of distributions are presented here with occurrence map with the occurrence records overlaid. Starting with zooplankton, for the 4 species of zooplankton, the predicted probability of occurrence are shown together with actual occurrence records, and as can be, the models performed reasonably well. The same is shown here for selected species of fishes. Again, the predicted probability of occurrence together with the raw occurrence records. And finally, for the bentos, the same story, the predicted probability of occurrence together with the raw occurrence record. Again, you can see the most of the model, the ensemble model performs reasonably well. Now showing on stacked speciesishness, starting from fishes, where for each period, starting from the present or contemporary period, and 2050 under low emission, 2050 under high emission, 2100 under low emission, 2100 under high emission. So the most visible change in the speciesishness for fish are shown or observed for the 2100 under high emission scenario. The same pattern holds for bentos, where a visible change in the speciesishness are observed for 2100 under high emission scenario. Here we show here the difference in speciesishness between a contemporary period and the 2050 under low emission, 2050 under high emission, 2100 under low emission, and 2100 under high emission scenario. Again, it's very clear to observe a substantial reduction in the number of species for the 2100 under high emission scenario over the shelf and shelf edge region on the south coast and also the west coast, but an increase in the speciesishness of Namibia and nearshore area of west coast of South Africa. Next, we see here the number of species that are expected to experience change in distribution area. That's an increase or decrease in distribution area, where the contemporary period distribution area of each species under each group are compared to distribution area under the low emission 2050, high emission 2050, low emission 2100, and high emission 2100. And you can see differential effect of climate change throughout the different combination of temporal window and emission scenario, but a substantial decrease in distribution area or contraction in distribution area for most species of bentos and fish are observed under high emission scenario and for the 2100 period. So just a bit of a summary of the result of this study. Maps of biodiversity for the three functional groups largely correspond to known pattern of speciesishness already published for this region. That will be true longitudinally and for the Khrushchev pattern. And we also saw differential effect of climate change depending for both emission scenarios and the two temporal window. But we see substantially more species experiencing contraction and distribution area at the high emission scenario for the period 2100. The traditional biodiversity hotspot on the south coast and shelf edge on the west coast appear to experience a reduction in species richness, whereas the nearshore area on the west coast and of Namibia experienced an increase in the number of species that is becoming more suitable to more species from South Africa. Thank you all for listening. I also would like to thank all that make possible the data used in this study. This was that with occurrence data from OVIS and GBIF, and involuntarily from BioOracle that are both for the contemporary observation and the projections.
Great, thank you, and thank you for sticking around for one last talk after this. We'll get started in about 2 minutes for that, just to let other people come back in if they want to do that. And a reminder to, if you're a speaker, check the app to see if you have questions, and if you would like to ask questions of some of the speakers and you don't have their contact information, I believe you can find that through here as well. Also, please come to the poster session this evening. Session 10 is in one of the rooms down there. It'll be a little bit tight, but there's a lot of good content there. I believe there are also posters that are only available online as well, and so be sure to check for those for people who couldn't attend in person, but there are a good number of posters that I think would be very interesting to check out. So, wait for another minute, and then we can get started with our last speaker. Thanks. Okay, great. Thank you, everyone, for staying for our last talk of the day. I'm glad to be able to introduce Sheku Sei, who's going to be talking to us about pelagic fish distributions.
Thank you very much, and I'm sorry for keeping you waiting. This is actually some work. We've started putting some data together to see if we can see some relationship between pelagic fish distribution and the temperature changes. We have commenced several hydroacoustic surveys using the Fridge of Nansen, the Norwegian survey vessel, for several years, and we are continuing to do hydroacoustic surveys to be able to get data to actually see the relationship, because we have very important fish stock, the bonga shad, which is not seen anymore in the small-scale fishery sector. And we've started implementing seasonal closures. We are thinking that, well, it's a shared stock in West Africa that other countries use, from Angola down to Cameroon. But we think there's some relationship between temperature changes, because nowadays we see some rising sea temperatures, as compared to the past. So we've started doing some studies just to look at the data. So I'm a PhD student at the Center for Marine Socioecology at the University of Tasmania. I've actually been doing my studies offshore. I've not been able to go because of the COVID and so forth, but we are seeing, myself and my primary supervisor is looking at some possibility to get to Hobart to actually do my studies. So I'm also a fisheries scientist and researcher. I'm an assistant director of fisheries in Sierra Leone, but I think I want to do some more studies to understand better. Next slide. Okay. The green? The green one. Oh, yeah. So why do we want to know about fish stocks or fish abundance and temperature variations? It's important because we've seen now shifts in climate regime, which is negatively impacting the fish populations, fish resources, and their ecosystems. The country has abundant fish resources, which the government depends on for revenue generation. So we think it's a very important fishery. So we are favored by two current systems. The Canary Current in the north, which is favored by the Guinea Current large marine ecosystem, and the Canary Current in the south, which is the Canary Current large marine ecosystem, and the Guinea Current large marine ecosystem in the north, where you have Guinea-Bissau down to Angola. So,
we want to see the actual relationship between, like I said earlier, increases in pelagic fish abundance and temperature distribution. So I will not bother you too much with the protocols of hydroacoustic surveys. All of you, most of you know, but we've been doing surveys using various platforms, the Fridge of Nancy platform, the Senegalese research vessel, and recently some Chinese brought some research vessel. We try to see, we do surveys during the rainy season and the dry season for both pelagic and demersal resources. But we are more interested in the pelagic resources to try to relate some temperature connections with distribution of fish. So this is just deck sampling protocols, the basic deck sampling protocols that we do in the sub-region. So we collaborating with scientists that come from either Norway at the Institute of Marine Research, or they come from Senegal or China very recently. So what we've been doing is to do some parallel transect to actually look at, we collect both environmental data, temperature, salinity, etc., and we also look at the distribution of fish stocks and the abundance. So we actually try to fish on schools during the acoustic surveys, and then we can characterize the catch that we get from various schools that we fish on to be able to assign SA values. The procedure is a long procedure. I don't want to bother you too much with that. So, but the target species we look at are the clupeids, which are very important in the local market, the small-scale fishermen, the pelagic fish resources, the carangies, the scars, the jacks, the horse mackerels, the sphaerinidae, the barracuda. Sierra Leone is actually, when you talk about Sierra Leone, if you go to Google and you type barracuda, they will begin to tell you how Sierra Leone is popular. It's a very big, large pelagic fish. It can grow almost to the size of skipjack tuna. So these are fishes that are more common in Sierra Leone and are highly valuable. So yeah, we also have some common, large pelagics, the tuna. We have the skipjack, the yellowfin, the little tuni, the big eye, the Spanish mackerel, chopped mackerel, etc. So we try to look at their abundance and distribution, just to maybe to whet your appetite, but you have more fish in Norway for people from Norway. But these are our commercial stocks. We have, most importantly, we also have some lobsters, very, very delicious, but we have all these kind of commercial stocks, which makes it important to actually do some studies. So like I told you earlier, we do some of these studies, try to identify species. We have experts from the region that go to Africa, West Africa, under some program in the Institute of Marine Research, Fridge of Nancy, to train scientists to be able to do some research and use the data. These are some of the data we are now using to locate some relationship. So, like I said, I will not bother you much with hydroacoustics. Some of you know already about that, but it's basically targeting the swim bladder of the fish, and then you'll be able to look at some SA values, apply some formulae to get the abundance. So we're able to get abundance using the acoustic data, and for various surveys, like you see, survey 1 and survey 2 up to survey 3. And we also got environmental data for those survey routines, temperature regimes, etc. So what is more important is that we saw the data shows some direct relationship between temperature increases and reductions in pelagic fish abundance. We have distribution of pelagic fish species of the clupeids and the carangies in the Sierra Leone continental shelf, which suggests that as the temperature increases, say above 26, 27 degrees, we actually see some decline that you see in the graph that I'll show you, some decline in the population and even the production of the fish from commercial catch data. We try to compare both the commercial catch data, independent and dependent surveys to see. So, but it was more pronounced in the Shabro Island. For some of you who may read about Sierra Leone, we have an island very popular, Shabro Island, tied to slave trade and so forth. But this is where we saw some pronounced temperature changes that were related to the abundance of fish. So if you see from 2014 to 2020, we look at the pelagic fish. The artisanal fisheries in Sierra Leone is more dominated by the pelagic. The carangies, the clupeids, they are more the artisanal
fisheries. So if you see the data, you'll find out that there are decreasing pelagic fish abundance as the surface temperature increases from 2014 to 2020. In recent years of 2018 to 2020, the artisanal catches, mainly clupes, have shown decreases in production as the temperature increases. If you look at the summary, for example, you find out that in 2018, we had landing production of 288, 229, and then the temperature, average sea surface temperature for its monthly average is 26.5 degrees. As the temperature actually increases, you find out that the production data is reducing, and when we run the analysis for maximum sustainable yield, it's coinciding. There's more studies to be done, but we are seeing already some interesting relationships between temperature increases and the abundance and production of pelagic fish populations. So, and further stock assessment show that we have these stocks now that you can hardly see in the artisanal sector. They are shared stocks. They are caught by Cameroon, Guinea, Liberia, Guinea-Bissau, Ghana, down to Angola. But now in Sierra Leone, you can hardly find them. So and these are very important pelagic fishes. So we suggest that the combined effect of rising sea temperatures and overfishing is critical for sustainable fisheries in Sierra Leone. So the study further shows that within the shallow zone of a major fishing ground, which is around the Banana Island, the temperature regime actually increased up to about 31 degrees centigrade. And down from the surface to 10 meters from the surface, we have those temperatures, which is actually going down. We suggest a convection, there must have been some forcing and mixing in the population of Karangic fish populations, because the Karangic fish stocks were decreasing as the temperature, the sea surface temperature increases further with depth. So the presence of an isotherm at deeper layers of 20 meters coincided with the nearshore and offshore salinity increases. We look some relationship between salinity, of course, temperature and salinity are dependent. The more there is temperature, the more there is reduced salinity, etc. So, higher salinity. And then when there is rain, you have reduced salinity. But the temperature variations were more critical for sustainability of the sheared Sardinella stocks, and also the horse mackerel fish, which is sheared stock in the West African region. The assessment results of our stock assessment shows declining fish populations, mainly the pelagic fish populations. So this cannot be unconnected with temperature fluctuations. So we have actually started doing some campaigns to be able to tell the communities, in addition to doing some seasonal closure. Every April and October, we close the waters to industrial fishing vessels, the trawlers. But we also want to extend it now to the small-scale fisheries, because they also, if they catch the juvenile fish in the inshore waters, they will not be able to recruit to the fisheries properly. So we want to implement alternative fish smoking, like climate-smart fishing, to actually reduce the emission of greenhouse gas to the atmosphere, just to see we do some effort to actually reduce the impact of climate change. We also look at mangroves that are very important to sequester CO2 from the atmosphere, 5 times compared to other plants. So we try to do planting of mangroves in degraded habitats. Thank you.
Thank you very much. We have some time for questions.
Hi, thank you for an interesting talk. Earlier today, when you were somewhere else, I think, we heard about species on the northeastern coast of the US where they were experiencing a decline in one area and an increase in another area. Do you see anything along the Western African coast here that when the Senegalian species are going down, it's going up maybe further south?
Well,
are they moving, basically?
Yeah, definitely. Like I said, we had a lot of bonga shad in Sierra Leone. Sierra Leone had more bonga than Senegal, but now Senegal has more bonga than Sierra Leone. So this is, in fact, the reason why we are putting together this large data. And you know, to be able to really look at, there must be some relationship of temperature increases, you know, and these temperature regimes are very important also for productivity. So it might not be negative all the way, that temperature can also favor abundance of species because of productivity, phytoplankton, etc. So these are all some of the relationships we want to look at in further studies. We've just started playing with the data, and I'm quite interested in looking at some of these temperature anomalies, and the distribution of fish in my PhD program is one of the chapters that I'll be looking at. Yet at very early stage, I'm putting together the data, but that's very important to look at. Yeah.
I'm curious if you are trying to bring in climate change into any of your stock assessments as you're starting to see these relationships, or thinking about that?
Yes. In fact, we had, with the Sea Around Us project, with Daniel Polo, at the earlier stage of my career, the stock assessment was leaving out environmental data. So what we are doing in Sierra Leone now is to do a regional approach, where we use, well, there is still data limited situation in the region, Sierra Leone down to Angola. So we pull some data together, but we implement them in environmental environment, where we use, for example, the Baudin model, the biomass dynamic model, to look at some environmental, where you can actually force the environment to be able to see the relationship. But this is very important in stock assessment. I think this is, in fact, the reason why, as a fisheries person, people say climate, so I say, oh, now I see my data, temperature is increasing and fish population, let me see some relationship. I think stock assessment we have to use environmental regime, and we have started doing that in the sub-region under the CCAF program to actually look at the impact of environment on fish populations and the sustainable yields. Yeah.
Any more questions? Okay, great. Thank you to our speaker. Thank you to all of our speakers today and yesterday. I think this has been a great session, and really appreciate everyone's contributions, including the audience's contributions. So thank you for attending, and don't forget to come and see our posters this evening. Thank you, everyone.